Hey everyone, today we will be implementing the automatic gradient system. So to do this, we're going to implement the tensor mechanism, right? So we're going to cover basically every single operation we care about in PyTorch. We'll take a look at what those are in a bit. As a quick prerequisite, we implemented these unified arrays last time, and these arrays were nothing special. It was just a wrapper that allows us to run CPU or GPU operations with NumPy only. And it was just a wrapper because it pipes our data through either NumPy or CuPy, depending on the device that we selected. So for the most part, we'll be using NumPy operations, but know that because we're doing them on these arrays, it'll work on either NumPy or CuPy, and we'll kind of see a little bit of that later on. To implement AutoGrad, there's actually quite a bit of stuff we need to do. We're going to go through it step by step, so hopefully it will make sense, but let's just do a quick recap here so we can present. There we go. So backpropagation, the entire point of backpropagation was we want to compute the derivative of the loss, typically, with respect to all the parameters in our model, right? All the parameters in our model. But that requires us to actually compute these derivatives, which means we need to define what these derivatives are. Like, what is the derivative of the loss with respect to y? Well, that depends on the function that we use for the loss. What's the derivative of y with respect to b? So what's the derivative of adding? What's the derivative of matrix multiplication, ... right? So we need to implement these operations. And we briefly talked about in our implementation of a transformer with absolutely no AutoGrad, so we did manual grad in that case, we saw that whenever we have some sequence of operations, like a sigmoid function, right? Sigmoid, you do e to the power negative, you do e to the power negative x, right? Then you add 1 to it and you take its reciprocal, and that's your standard sigmoid. But that requires us to do the automatic differentiation through each one of these operations. And these are some of the operations we are going to support, right? Taking a reciprocal, squaring, to be able to, do an exponentiation, multiplying by -1. So these are some of those operations that we want to do. And the entire idea behind AutoGrad is as long as we can describe our complex functions as a composite of a bunch of really, really simple ones, then we can perform AutoGrad. And that's the idea. Now, we also saw that AutoGrad is not ideal. Whenever we have known composites of operations like the sigmoid function, this is kind of a bunch of wasted computation, right? Doing the backpropagation through this stuff. It will give you the correct answer, but if we can avoid it, then we should. And that's why we have these here. To basically give the manual backwards from the output with respect to the input. We won't be implementing this today. Our goal is just to create all of those tiny little functions upon which the rest of our system will be built, right? So we'll see all of that later. So what operations are we planning on doing? And you can essentially describe all of the operations and neural networks under these 4 branches, right? So you have binary operations. So those are like adding, subtracting, divide, multiply, matrix multiplication. So you have 2 different things, right? You basically have 2 different, like some x and y, and you can add them together, you can subtract them from each other, you can divide, multiply, whatever it may be. We have unary operations, and these are element-wise operations. So you apply some operation to every single element in your matrix or tensor, whatever it may be. And so, here's the list. We can exponentiate, we can take the log, we can do the absolute value, we can clamp it, the square root, the sine, cosine, tangent, or the, power. And looking at these, right, looking at some of these operations, these don't look all that bad, right? We know what the derivative of all of these individual tiny operations are, so we can just implement them. That's kind of what we'll be doing. There are reduction operations, and this is typically like if we have a 10 by 10 matrix and we take the average across the rows, right? Or just take the average of the entire matrix. And so reduction operations typically entail having some matrix, and you do some type of summarization along one or more axes, right? So standard setup there. And then we have indexing and reshaping, right? And this is also pretty straightforward, but we want to be able to index our data. We want to be able to transpose or permute, reshape, flatten, squeeze and unsqueeze, which is adding or removing a dimension, concatenating data together, stacking data together, and chunking data. So these are kind of all of the standard operations that we're going to need to implement. So this is basically the list. We will be implementing every single one of these things. And once we do a couple of them, we're going to get into a groove, right? It's not going to be very hard. But that's what makes this kind of a long video, because there's just so many operations. There's a couple of extra ones that are helpful to have, right? Masked fill, sorting, and arg sorting. So we'll just kind of toss those in there I don't think we really use the sort or argsort anywhere, but the mask fill we will need for that causal mask, right? For transformer stuff, so that's fine. So we'll come back to broadcasting later when we actually start exploring those things. So there's going to be, let's go here. Let's just start implementing, and we will refer to things as we go. So the entire setup, so last time we wrote this file right here, right? So this was our array that we wrote. And again, the array basically allows me to do NumPy operations on GPU tensors by just homogenizing NumPy and CuPy. There's nothing fancy about this, so we're not going to worry about it. Again, you can watch that video, and that should be fine. The other thing that I just copied in are these. These are going to be my supported D types, right? Float 16, 32, 64, standard set. I didn't include any like complex D types or anything because that's fine. We don't need to do that. That's what PyTorch is for. This is supposed to be just an example. Maybe I'll add it in later. That's fine. So let's just start with some inputs. So we're going to need NumPy. So we'll be using NumPy, but again, the entire system will work on GPU as well, which is what that array mechanism does. We're going to need something called WeakReferences. You may not know what this is, but this is going to be super important. We'll see what it is later. From func tools, we need wraps, and we need, let's see, from context lib, import the context manager, import context manager. We're going to write a decorator later, right? So with torch.noGrad, we want something similar. We'll add that in. We need a warnings. We need from dot import array. And for now, we won't do dot. We'll just do import underscore array as AP. We won't run them as modules for now. And then from D types, we'll just import all the different D types that we have. And there we go. So tensors are pretty straightforward, right? We're going to do class tensor, and this will be the bread and butter, right? The system that does literally everything in our AutoGrad. So first, we're going to throw a build graph, and by default, we will build the graph, and we'll just leave that in there for now. We'll come back to that later. So every AutoGrad, so every tensor needs a couple things. What is the data? And these are going to be those arrays. When we do it, do we want to require grad? Requires grad by default will be false, just like in PyTorch. We have a grad function, right? So if we do if we compute something, if we do something, what is the grad function that created it? What is the grad function name? We need the device, which we'll set as none for now, and then D type also as none. And we'll kind of see how all of these things play a role a little bit later. So our self.data is just going to be ap.array. We're going to give it data equals data. Our device equals device, and our D type equals D type. And again, the array mechanism that we wrote last time will handle everything: device placement, D type management, all of that. That's why we wrote it, just to make our tensor class a little bit simpler. We could have put all of the array stuff inside the tensor, but it just makes it more annoying to explain. So we just separate it out. We'll have requires grad is requires grad. We'll have self.grad function is our grad function, self.grad function. And here, these are just copies, right? So we can just put that right there. Okay, so we have our grad function name, and we have grad. And every tensor, what makes a tensor different from the array is it has the ability to store some gradient, right? So this grad by default is none because, again, at the start, we don't have anything. But then later on, when we actually compute gradients, that'll show up. We're going to have something called leaf, self.is leaf. And this is going to be self.requires grad, and self.grad function is none. So a leaf tensor, right, is basically something that we created, right? So a tensor that we create, for example, the let's say the weights and biases of a linear layer. When we first create it, it doesn't have a grad function, right? The weights and biases were not created from some operation, they were just created. So basically you can imagine that the beginning of our computational graphs, or the parameters, are these leaves. And we'll kind of take a closer look at that later. We'll have self.parents, and this will be an empty tuple for now. Parents are where we're going to store. This operation was created by these input tensors, right? So if we add two things together, these are the inputs that we added together to create this output. So the inputs are the parents of the output, right? They are what created them. We'll have self.retain grad is false. And actually, we'll maybe leave the retain grad out for now. Yeah, we'll leave that out for now. We'll come back to that later. It's just kind of a detail that doesn't actually matter for what we are trying to do. And if you remember, in our array, we wrote all of these different properties, right? Like what is the backend device? So xp can be either np for numpy or cp for cupy, right? Either one is valid. So we have kind of all of these different properties that we created last time. So let's just go ahead and add some properties in here as well in the same way. And if you don't remember, properties are basically a view of data. I cannot set my property in another way. So, and maybe I'll do this one specifically just so it's clear. So this just lets me access what is the xp. Remember, self._data is an array type, and that array type has an xp, has a dtype property, a device property, shape property, a number of dimensions, all that sort of stuff. So all of these properties kind of exist already. One more property we're going to add in is our data property, right? So we're going to do at property, and this can be def data, and we're going to pass in self because it doesn't matter. So this is going to be like if we want to view the data of something, then we can do return self dot data. That's all. And then if we want to update the data, which is fine, we can also do at property def data self value. And this won't be just property, it'll be property it'll be data dot setter. So this data dot setter, this data refers to this data, and this is a setter because I'm able to actually update this specific property value. These are just little details. We don't really need this, it just makes it nicer code. So ap.array, and it's going to be the value and returned self. So all we've done is data is a view. If we do tensor.data, that's a view of this. But if we want to update that specific data, we can do tensor.data is equal to some value, and that's going to go ahead and trigger this and actually update that data value. So there we go. Nothing crazy. We also have some pretty printing, which is not that interesting. So this is just like what we had last time. So I'll just paste this in so we can see it. This is just supposed to make it look like PyTorch is printing, right? So we can print out our array. We saw that NumPy and CuPy have this array to string method where it can just print your data out in terminal, and we'll see what that looks like in a bit. And then we're also going to add in some extra stuff, right? We're going to make it look like Torch. So we want a requires grad. If it's there, we want to know what device it's on if it's not on the CPU. And basically we'll get something that looks like Tensor. Here's the data. Here's my gradient information. Here's my device information and all that. So this is just housekeeping, not that interesting. And in our array method, right, we wrote a to, right? We wrote a to method already, which can take some tensor and move it to somewhere else. And so this is just going to be self.data is equal to self.data.to device. And we can return self. And that's it, right? So this is just something that we'll use, again, one of our built-in methods that we wrote in our array, right, to move stuff around. This is why it just makes it easier to move the array outside, just because it just makes life easier. So there we go. All right. Lastly, we need a, let's see, we can come back to that. We are not going to write the backward pass just yet. We are going to work on our first operation. So like I mentioned, there's a bunch of ops. We're going to start with binary ops because they're easier. They're all pretty easy actually, but this is where we're going to start. Binary ops. So the first method we want is the add method, right? Self val. And so basically, this is going to be the output, right? Well, I'm going to try to write out the operation for everything we do. It's going to be a plus b, right? Where a is going to be our self and b is going to be our val. So that's all we're doing for this operation. So what is do dA? Well, that's just one. And what's do dB? Well, that's also just one. So dL dA is going to be do dA times 1, because it's going to be dL dA is do, it's going to be dL do. There we go. It's going to dL dA is going to be dL do and then times do dA. Right, that's our standard setup. And this is our upstream gradient, right? Coming from later in the model. If we go back to this figure right here, right? We want, for example, if we're doing sum, we did A plus B1 is the sum. These are the two things we added together. So we know that the derivative of dH dB1 is just 1 because it's just a sum. But the derivative of dL dB1 is dL dH dH dB1. And so that's all it is, right? It's going to be dL dH times 1, which is just dL dH. So nothing crazy. So this is just going to be equal to dL dO. And then in the same way, right, dO dB will be the same thing, just also times 1. So how we're going to set these up, how we're going to do every single one of these, we're going to do if is instance, if our val is a tensor, no problem, then we're going to do self dot, first a quick method for check broadcast, self and val. So this check broadcast is just going to make sure that we can actually add these things together. And so let's just quickly write that method up here. This is a static method, at static method. And this is going to be def check broadcast. And in check broadcast, we provide two things, A and B. And in A and B, we're going to check if the len of A.shape does not equal to the len of B.shape, and A dot requires grad and B dot requires grad. I think that's all it is. I can just paste this thing in here. There we go. So this is our check. If A and B are not the same shape, and A dot requires grad and B dot requires grad, then we actually make this an incompatible operation. So here's the idea. We're going to be dealing with broadcasting quite a bit in just a bit, but here's the main idea. If we have a tensor that's 1 by 3, and we're going to add to it just a 1 number, this will actually work in NumPy just fine. This will just add this 1 value to each one of the 3 values in this one, and that'd be fine. What I'm saying is that I want to explicitly make sure, and so this would be a 1 by nothing tensor, and this would be a 1 by 3 tensor, right? Those would be the shapes of it. I just want to explicitly make sure that the number of dimensions in this is the same as the number of dimensions in this. And this is just a simplification to make my life simple, life easier. And it's fine, right? It's not that big of a deal. So we just need to make sure when we add things together, if we're doing broadcasting, the number of dimensions are the same across all of them. So this is okay. This is not okay. And we only care about this because in the backward pass, you'll see we're going to have to actually care about the broadcasting. And this just makes it easier for us to kind of set things up. And it's not that hard to make sure data is the same shape before you actually do it. So let's go ahead and just keep going. This is basically our check broadcast. Are they broadcastable? If they are, right, then we're good to go. We can do val data is going to be val.data. And then we're going to do val requires grad is going to be val.requires grad, because these are tensors, right? So basically I'm extracting what is my underlying data array for this thing. What is my flag? Do I require grad here? And then we can do val shape is equal to val.shape. So this is me saying I want to add something to myself. And I'm just making sure here, is my val a tensor? If it is, well, here you go, right? If val is a tensor, we're good to go. Otherwise, if it's not a tensor for adding something else, then we're going to just go ahead and just convert it to an array. Like if we're doing a scalar, right, just +2 or something, then it'll be val dtype is going to be self.dtype. We're going to make sure the dtype's mass, and then the device is self.device. Just create an array with just whatever it is, and that's what's going to go in here. And if it's not something we support, if we're trying to add like a list to the tensor, this array will already throw an error saying like this is not something we can process, right? So that we're good to go. By default, if we're not adding two tensors together, then the thing we're adding cannot have any gradients, right? So it requires grad to be false, and val shape, let's just say it's none here because we don't know what it is. All right, so our output, all right, our output is just going to be np.add self.data and val data. And that's it. So this is me using NumPy methods, but these things could be sitting on GPUs. And again, my array module will handle the mapping and make everything work out. And that's it. That's my forward pass, right? I just took two tensors and added it together. There's really nothing else going on here. And so now here comes the important part. How do I do my backward method? I will be using closures, right? So we're going to do add backward. A closure is basically, I'm going to have a reference. Let's do input grad. This is going to be our upstream gradient. So again, going back to this figure, the input grad would be if I want DL dB1, can compute dH dB1, so my upstream grad would be dL dH, right? That's my upstream gradient right here, so my input grad. And what we're going to do is if self.requires grad, so we only want to do these things if it actually needs grad, we need to do one thing first. We need to deal with broadcasting. And this is where it gets a little bit complicated, but not too bad. We're going to do self grad. It's going to be self.broadcasted grad accumulate, we haven't written this yet, of self.shape and our input grad. So let's kind of get an idea first of what broadcasting is and why we do it. So I have a figure right here. So broadcasting is when we want to add, if I have a 4x3 matrix here, X, and I have a 1x3 matrix here, Y, and make sure, we ensure that they have the same number of dimensions, just to keep it simple. Then when I add these things together, that's going to create a 4x3 because NumPy and CuPy will automatically broadcast this tensor along this one. It'll just add it together. And what it really looks like is this, right? Basically, broadcasting is just creating a repeat, right? Repeating this tensor over and over again to match the dimension of this tensor, and then you just add it all together and we're good to go. But when we do the backward pass, right, we need the derivative of z with respect to x and z with respect to y. Those are the two derivatives we need. So with respect to x is easy, right? We have dl dz, that's my upstream gradient, and I want dl dx. And because these two things are the same shape, we're kind of good to go, right? The shapes of these gradients will match, and we're okay. And so again, just going back to here, basically the shape of this and the shape of x, so z and x are the same shape. So the gradient with respect to z and the gradient with respect to x will also be the same shape because the shapes of the gradients have to match the shape of the actual tensor that we want to update. On the other hand, how do we do this? If dl dz is a 4x3 tensor, but dl dy is supposed to be a 1x3 tensor, how do I match these? What do I do? And this goes back to one of those ideas we talked about earlier in our implementation of the transformer. Whenever we have something like this, we added dl dy to different parts of x, right? So basically added y to x in different positions, right, along that dimension. Which means during the gradient, when we compute the gradient, we'll get different contributions from the different x's, right? The different contributions, from the input gradient. And because there's different contributions, we can essentially say that because the tensor we actually added was this, it's just these things all are the same tensor. We just copied them. And so each of these things are going to get its own gradient. And those are kind of the individual contributions across this tensor. And then because each of these things have their own contributions, we can go ahead and accumulate up all those contributions and just sum them together. And that's basically the main idea for broadcasting. All we do for broadcasting is we take a tensor and we get the gradient in the shape of that tensor, and then we go ahead and just sum up along all the broadcasted dimensions. In this case, we'll sum up along this dimension and get us that final 1x3 dl dy. And that's it, right? That's broadcasting. It's how we accumulate the gradients. So let's go ahead and implement that. Very, very simple. All we need to do, and this is why we check broadcast, because if we make sure that the number of dimensions are the same all the time, then it's fine. So the only thing that can change is the dimension itself, right? So we can see this is 4 and this is 1, but this is 3 and 3. So I know that this dimension, the 1 dimension, is the dimension that we broadcasted along, right? Because it's less. It's that's what we did. So let's go ahead and write that method. This is going to be def broadcasted grad accumulate. It's going to take a self. It's going to take a shape, right? What's the shape? And then x grad, the actual gradient itself. And we're going to do grad shape is going to be x grad dot shape. So this is, in this case, the upstream gradient, and that's its shape. And like we did before, but we can throw another assertion error here just to make sure it's all good. We're going to make sure the len of x shape is equal to the len of grad shape, right? That's our sanity check. And now what we're going to do is figure out what are the axes that we need to sum over. And by default, when we do broadcasting, basically the dimensions that we're broadcasting have to be 1, right? So when we do it, NumPy will look at this and say, oh, this is a 1x3 and this is a 4x3. So this is the 1 dimension. This is the dimension that I want to repeat. So we can easily check for that. We can do sum axes, what are the dimensions that we summed over, or whatever it may be, whatever broadcasting we did, but in this case we're just going to call it sum to keep it simple. We're going to index for index and xdim, graddim in enumerate zip our x shape and grad shape. We know that the grad shape will be larger, so we know that the grad shape will be the shape of the full output tensor, but the actual grad that we want will have a 1 in that place, and that's basically what we're going to check for. So it's just going to be the standard index if, so basically what we want is index if, here we go, if xdim equal 1 and graddim does not equal 1. So as an example, if we have a 4x3 like we did, and then a 1x3, right, 1x3, what we want is to add up the gradients along the 0th dimension, right, where it's different. But everything else is fine. We don't need to touch the other dimensions. So all we're going to do is just create that. We want the dimension, so index will be either 0 or 1, because how many dimensions does this thing have? There's 2, so it's just index 0, index 1. And then it's just going to be the index if, right, basically keep the indexes if these conditions are met. If my dimension here is 1 and this is not 1, then this is something that we broadcasted over. And so that's all this is doing. It's just identifying those dimensions, and we are good to go. So now that we've identified the dimensions, this would return back sum axes would just be 0, right? That's it. If we had a slightly more complicated example, like if we had 4, 3, 2, 8, and we had 4, 1, 3, 1, 8, well, we then would have broadcasted along this dimension and this dimension, right? Both of these would have been, and then our sum axes would have been 0 because we broadcasted along this dimension, and then 2 because we broadcasted along this dimension, right? The indexes. There we go. And let's not make this, let's make it like 7 or something. So it's 0 and 2. So the position 0 and position 2. And that's it, right? That's our sum axes. And now that we can do that, if sum axes, so if there was no broadcasting, like everything was exactly aligned, then there's nothing to really do. So only if we have some sum axes, then we're going to do xgrad is going to be equal to np.sum, and it's just going to be a reduction, right? We're going to take xgrad, and axes is just going to be a tuple of the sum axes, and we're going to do keep dims equals true, right? We don't want to lose those dimensions. We'll just have dummy 1 dimensions in those positions, just so things stay uniform and simple. And there we go, right? Nothing too crazy. We just added up those gradients, and this is just doing exactly what we described here. We have this tensor. I know that the 1 dimension is what I want to sum over, so I sum over the number along this dimension, right? This is the 0 dimension. This is the 1 dimension. It's the 1, the 0th position, the 0th index that was broadcasted over, so sum over the 0 dimension. That's it. So this goes ahead and just checks if we did any kind of broadcasting. If we did, then good. We can just go ahead and set it up that way. And now we can do if self.grad is none. So by default, what we're going to have is our gradients. We saw it right here, right? Our gradients start as none. So initially, if there is no gradient, then just go ahead and just set our gradient as what we computed. So it's going to be self.grad is equal to self.grad. Else, if it's not none, and this happens in gradient accumulation, right? If we do multiple backward passes, we want to sum all those gradients up together, right? We want to accumulate those gradients. And so all we're going to do is self.grad plus equals self.grad. And that's it. Nothing too crazy. And now that we've done this, right? Now that we've kind of completed this, we don't need self.grad anymore. It's stored in the self.grad. We can go ahead and just clear it out, right? We don't need this, so we'll just delete it. In the same way, if val requires grad, and this should be, yes, so if val requires grad, because remember, we are doing an operation like this. If we go back to our linear layer, so we have a sum right here. We just checked if the sum was c plus b, we know that c requires grad because we have to keep going backwards, right? We need to keep going backwards to continue, backpropagating. But we also need we also know that b requires grad because b is a learnable parameter. So both self and val, or just one, or none, like any combination of them, could require grad or not require grad. So we're just doing our check. If it requires grad, do it. If it doesn't require grad, there's nothing for us to do here. And so we can do val grad is equal to self dot broadcast grad accumulate just like before, but again, val shape and the input grad. So just like before. And then again, if val.grad is none, then we're going to do val.grad is val grad. Else val.grad plus equals val grad. And that's it. That is our backward method, because that's all there is, right? There's nothing fancy. So add is very simple, right? Add basically takes gradients and just copies them to both branches, right? Both the inputs, assuming they both require grad. And so now we have our forward output, we have our backward method. So let's just kind of see how we can put it all together. So requires grad is going to be equal to self.requires grad or val requires grad. So if either one of our inputs actually required gradients, then we need to essentially, the output then will also require gradients, right? That's it. So if any of the inputs require gradients, then the output also requires gradients. And our output is equal to tensor output. We'll have require. So basically, we're going to take the output, which is currently an array, right? It's just an array. We're going to rewrap it in this tensor, and that's all. So requires grad is going to be requires grad. Our grad function is going to be the add backward. So what we're doing is storing this method. And remember, this method is a closure. So even though I'm storing it here, it has a reference of self and val, right? All of that is referenced inside here. So we're good to go. And so now that we have all of that, we have our grad function. We only need the grad function if requires grad, else none, right? If we don't need it, we don't need it. And then the grad function name is going to be, and this is kind of up to us, I'm going to call it add backward, just like that. If requires grad, else none. And then the device, we want to make sure it goes to the same device, right? Wherever it was, it'll do that. And in this case, because if we're computing on the GPU, then the output will also be on the GPU, because that's how we wrote our array system. And so up here, basically this will be a no op, right? It'll just, the array system will see, oh, I want you to move it to a GPU, but it's already on a GPU. So there's really nothing for us to do here. Okay. And that's almost everything we need. There's two small details that we're going to have to keep track of. The first one, and this is the easy one, is we're going to add this extra flag in here called build graph enabled. And this is just so we can actually use our build graph method. So up here, we have this underscore build graph, nothing fancy. And this just means if we are doing the forward pass, build the graph, right? Build our computational graph upon which we will do our backpropagation. And we'll kind of see exactly how backpropagation comes together later when we look at topological sort. But that's fine, right? Build graph. We just want a method to access it, and only if build graph is true do we want to do it. Because remember, in PyTorch, we have a with torch.torch.noGrad flag. Well, we'll be creating exactly the same flag, and that flag will toggle this, right? It'll turn it off when we don't want to compute gradients. If we don't want to compute gradients, we don't need to build the graph. So we can just quickly add in a class method that just lets us see that, right? So there you go. Build graph enabled. It's just going to be cls.buildGraph. And that's it. It's just a flag. And this would be true when we want to compute gradients, and it'll be false when we don't care about computing gradients. And so all we need to do here is just add that requirement in. So if we are requiring grad, that's totally fine if any of these, but we also check and tensor dot build graph enabled, right? Just check. So we only care if we actually want to compute the computational graph. If we don't, then this will just all be false and we won't compute grad at all. This just saves some effort. The other thing is we need to store some references. So if I compute, and this kind of goes back to this figure here, or this one right here, whenever I do some operation, I need to store, in this case, let's say z is 1 plus y. For me to compute some gradients, that's not a good example. Let's do O, right? We want to compute dO dz. I need to compute negative 1 over z squared. But for me to do that, I kind of need to store z, right? I need to store that z is the parent of O. Z created O, right? O came from z. So I need to just store that z is the parent of O. And this will let me compute create that computational graph, right? How are my different operations related to each other? And we'll kind of see in more specificity how that works out later. In the same way, right? In this figure that we've been looking at, right? Y is C plus B. So C and B2, right? C and B2 are the parents of Y. So we need to go ahead and store that so we can use that information for our backpropagation later on. And this is also pretty easy. What we're going to do is output, or we're going to do if requires grad, because again, we only care about this if you require grad. Output.add parents self val if is instance val tensor else none. Right, so this is going to be a method we're about to write. And basically, it's going to add the parents. And in this case, the output here was created by self and val, right? Self and val added together, and they created this output, which means we're going to add those parents to here. And we can now return our output. So let's go ahead and write this add parents method, because we're going to use it basically for every single operation going forward. So it's super important. To write add parents, it's almost simple, except it isn't. So we're going to add parents self. We're just going to pass in a list or tuple or whatever of parents. We're just going to pass in something. And we can first do if not is instance parents. If it's not a list or a tuple, that means there's just one element in it. That's fine. We can just make sure our parents is just a tuple of one thing, right? Nothing crazy. And we can do now self.parents parents is equal to, and this is going to be another tuple. And it's going to be P for P in parents if P is not none. And this looks like it works, right? So what I've done is I've stored, and remember at the beginning, we created this variable called parents. And a tensor that's been created from other tensors has parents. In this case, y was created by the sum of tensor C and tensor B2. That means the parents of y are C and B2, and we need to store that for that backpropagation, right? Otherwise, how can we do it? The problem is Python's garbage collector. This will completely consume your memory, and this is probably the most annoying bug that I worked with and then figured out. We cannot use standard references. We need to use something called weak references. Otherwise, this will not work out. And this has to do with basically reference cycles. So let's just kind of explore that a little bit. So reference cycles lead to memory leaks, and this is a limitation of the garbage collector. So we can see that a tensor will have some grad function which references some parent tensors. And kind of better example is this. We have some tensor C that has an add backward, right? Add backward is the method that we're using. And add backward, as we saw up here, has a closure reference to my self and val. So we can see add backward in here has a self and a val. And this self and val came from outside of the function. So Python closures essentially just remember the context inside which this function was created. And we store this function here. So we're using closures to basically do everything. The problem is that if we have a self and a val reference here, that means the add backward method references self and val. So we have a reference. Right? A and B are referenced in add backward. But I need to store that A and B, the tensors, right, self and val, are the parents of the output. So we have another reference here, right? Tensor C stores that its parents are A and B. And we have this thing known as the reference cycle, because tensor C has this add backward, which references A and B, and then A and B are referenced again as a parent. And so these are reference cycles. And Python's management of the reference cycle is not very good. In the garbage collector, it's very slow, and most likely it won't actually handle it. It'll just cause memory leaks. So let's just do a quick demo of what weak references are. So I created this here, so we'll just copy this out for now. In Python, they have a sys.getRefCount, right? This is a method that you can basically give it something, and you can see how many internal Python references it has. And let's just kind of look at that real quick, and this should make it very clear of why we need weak references. So we're going to do Python reference counter, and actually, let's just kind of talk about it. What I did is I just created a list. Reference counters have to work on your own types of objects, so they don't really work on lists, but that's fine. We have our own tensor object, so I just created a dummy class here that just stores some data, nothing fancy. And A, when I create A here, this is one reference. This is a reference to this specific object. Now, even though there's only one reference here, it's going to print out two references, and that's just because when we actually go to print something like another, when we're actually running this thing, another reference is just spontaneously created for this operation. So there's really one, but it prints out two, and that's fine, right? No big deal. So let's just say there's 1 for now, even though it says 2. So A has, this object has a reference. Now if I do B equals A, that creates a new reference, right? A brand new reference right here. So now we can see it iterated. We went from 2 references to 3, or 1 reference to 2 references. Now here comes the problem. If I delete A, if I get rid of it, notice that our reference count doesn't go to 1 or 0. It's still stuck at 2. Because even though A has been deleted, B is still making a reference to A, which is making a reference to my list. And so even if I delete something in the middle of the cycle, I can't get rid of it. So in the same way, if I deleted tensor A and tensor B, because once we compute the backward method, we don't need to store these intermediate representations. We're done. But even if I delete this, because of the reference cycle, Python's garbage collector doesn't know what to do with it. And so because it doesn't know what to do with it, it will end up just caching it, and it'll be stuck, and it will lead to memory leaks, and you won't be able to train any model at all. And so the only way to deal with this is with weak references. So what we do here is instead we create a same list, right? So we can comment y'all out. We don't need it. We create some list C, and then what we're going to do is C weak is going to be a weak reference to C. And what you're going to see here is that our number of references don't increase. A weak reference does not increase the reference counter, and that's what makes it a weak reference, right? After that, we can then create a strong reference. So D is a strong reference to C. And then we can delete C and then delete D, and you'll see exactly how this works out. We can see that we have no changes in the number of references. After we do a strong reference, our reference counter increases by 1. But then when we go ahead and delete D, which refers to a weak reference, our weak reference number goes down to 2, and our weak reference now no longer points to anything. And so this is just Python, right? This is just a limitation of Python. This is why in like C and stuff, you get such minor control over the memory allocation and stuff like that, right? You can reference and dereference things however you want. But this is how we have to do it in Python. So we just want to make sure that, as a quick summary, right? We want to make sure that these parents are not stored as a strong reference, but rather a weak reference. This way we don't add to that reference counter, and when I actually delete tensor A and B, there's nothing holding on to it, and so it can be garbage collected, right? Because it will only have 1 reference here. If we delete these things, so for example, if we delete these 2 things, then the weak references don't matter. These will go away, and this add backward no longer is pointing to anything, so those will go away, and there's basically nothing left, and these tensors can go ahead and be garbage collected, right? That's the important part. So all we need to do, and this very, very small change, instead of storing these references, P for P and parents, these are strong references, right? Instead of doing P for P and parents, we're just going to create weak references using weakref.ref P for P and parents. And this lets us access those things, but we cannot actually, it doesn't iterate the reference counter. And just one quick thing, if we actually want to view something, notice it's C weak parenthesis. So C weak, if we print, let's get rid of view, print C weak, this is going to say it is a weak reference to my list. But if we actually want to see the thing, then we have to unpack it, right? So we can use that, and this now becomes the actual mylist object. And that's it, right? So that's why later on you'll see we kind of use that technique. Okay, so nothing crazy, just little, like I said, lots of little details to get this to work out correctly. But this goes ahead and adds our parents, and so let's just give this a quick test. Obviously, this is just adding, so there's nothing of interest, and we actually haven't written a backward method yet. That'll be one of the last things we do. For now, we're just going to keep going and just test it out. We're going to do if name is main. We're going to create array. Let's do a is going to be equal to ap.array. And let's do ap.array.ones, right? And let's just create a shape of 1. So if we print out a, we should see that we have Python tensor.py. So there you go. It's just an array with 1 number, nothing crazy. We'll create a b. Let's just make it 2s. So now we have an a, we have a b. There we go, just 2s. And we're going to add them together. Now to add them, we're going to make a is a tensor a, and b is a tensor b. So this should run. Let's see if there's any bugs. No. So if we print out A, you'll see that. And this will now use our, that's our wrapper. That's all it prints out. If we set this to device equals CUDA, then you'll see it tells me which device this GPU is currently on, or which device this tensor is currently on, but that's fine. We don't need to worry about that for now. And now, because we've implemented this add, right, this add dunder method, our tensors know how to add things together. So we can now print, let's say C is A plus B, and we can print out C, for example. And you'll see it has this stuff right here, right? Just 3, nothing crazy. Now, what about this requires grad, all of this stuff here? We need to add that in, so we can do a requires grad is true on one of them. And you'll see that we now have this grad function for add backward. And the reason, again, this stuff is printing out is because I included it in here, right? In my print of the array, I add that extra information, right? What is the grad function? And I just kind of concatenate that all onto my tensor. So now we have our tensor and its grad function. And that grad function is what we're going to use for backpropagation later on. Now, a problem we have is this. If we try to add, if we don't convert A to a tensor, this will throw an error, right? Like we can't add stuff together that that's unsupported. So we have our radd method. So we're not going to worry about U anymore. We can just get rid of U, that's fine. So we have add, no problem. We also have our reverse add, self, val, and reverse add. Remember, add is not an ordered operation. A plus B is the same as B plus A. So we can now just return self plus val. And this will just try it the other way around in case, and this should be R add, reverse add. And there we go. All right. So let's just, I'll just put like this here. So remember, there we go. All right. So it just reverses them just to try the other way. So for example, if A is an integer and B is a tensor, Python integers, right? So if self is an integer and val is a tensor, Python's dot add, like the integers dot add, if we do like 4 plus some tensor, 4 dot add tensor will not work because Python doesn't know how to handle my tensors. So the radd just reflects it. It does it the other way around. It'll be tensor.add, right? It'll run my tensors.add, and then it will do 4. And I know how to handle integers because remember in my add method right here, I change it, right? I convert it to the array that it's supposed to be. So everything is handled in my end. So that's when radd will actually trigger. But we don't need to worry about this. That's basically it. We are not doing in-place operations. That's fine. Keeping this simple. Now we have our sub, def sub. And honestly, this method will be identical. So let me just copy stuff in. Right? Let me just copy, because otherwise this video will be way, way, way too long for me to type all this out. Let's just, let's tab you back. There we go. Sub is the same as add, but now output is A minus B. So that means DODA is 1, and DODB is not 1, but minus 1. Okay, so everything else is the same, right? Nothing changed. Our output is just going to be np.subtract self.data and val data, subtract one from the other. We're doing the exact same broadcast, grad, accumulate on both of them. But now, instead of just doing the accumulate on input grad, so self, remember, DODA will be 1, but DODB will be minus 1. So we're going to do the accumulate on negative grad, and that just handles it, right? That is nothing fancy. And then everything else here is the same. Our sub is a ordered operation, right? A minus B is different from B minus A. And so we just need to make sure we do that. So we're going to just take self and val, means we initially we're trying to do self minus val, but self minus val didn't work. So it tries to do val minus self, but in this case, because it reflected it, val will be the self and self will be the val. And so we just need to go ahead and multiply our self by the -1 and add it to val and just do it that way. That's also fine. So it's an ordered operation, right? So we need to make sure we keep it correct. Okay, that is our subtraction. Nothing new. So I'll try to, for operations that kind of are exactly the same, we're not going to type it out. We'll just kind of walk through it just to keep this video in some meaningful length. Okay, multiplication. This is super important. Mul, self, and val. Okay, So this is going to be O is equal to A times B. So that means DO, DA is equal to B. And DO, DB is equal to A. And you can see it's basically a switch operation, right? If we do DO, DA, we want the other one. If we want DO, DB, then we want A, and that's basically it. And again, this is what we really want is DL, DA. So it's going to be DL, DO times DO, DA. And then in the same way, we want DL, DO times DO, DB. So that's going to be DL, DO times B, and DL, DO times A. So our upstream gradient times B, upstream gradient times A. So that's no problem. We can go ahead and implement that. This won't, again, look all that different from what we've just done, but we can do, again, I'll copy repeated parts of the code because I don't need to type it. Right, so again, we're going to check, is val a tensor? Is it not a tensor? We're going to go ahead and multiply np.multiply data and val data. That gives me my output. So now let's write our mul backward. Def mul backward. And we have our input grad. And so we're going to do if self.requires grad. We need self grad is going to be np.multiply input grad times val data. Why is that? Because remember, it's the input grad. If we want the derivative with respect to self, which is A, it's going to be input grad times B, and B was val data. So there you go, right? So we're doing, in this case, we're doing, let's just make it clear. We did output is equal to self times val. And so the derivative of output with respect to self is the upstream gradient times val data. And then vice versa, it'll be the same thing for the other one, but it'll be the input grad instead, or the self instead. So we can first do self grad is equal to self dot, again, broadcasted grad accumulate, self dot shape, self grad. And we can do if self dot grad is none, right? Just like before. We're going to go ahead and set it self dot grad is equal to self grad, else self dot grad plus equals self grad. And then in the same way, we can go ahead and do self grad is none. We don't need you anymore. Now we're going to do if val requires grad. That's also fine. Everything else will be exactly the same. So we're going to do val grad is going to be np.multiply input grad and then self.data, right? Because it's just going to be the derivative with respect to val is just self. So it'll be the upstream grad times self. So times self.data. And then val grad is going to be self dot broadcast grad accumulate, again, val shape, val grad. And we can do if val dot grad is none, then val dot grad is equal to val grad. Else val dot grad plus equals val grad. And we can go ahead and just set this to none. Right? We don't need it anymore. And that's basically it, right? So that's the entire setup. And then everything after that is, again, identical. This part will always basically be the same, right? So there's my mul backward method that I want, only if I want to require grad. And I go ahead and add the parents, right? The parents of this operation will be the self and val that we multiplied together. And then in the same way, we have r mul. And multiplication is not an ordered operation, so we can do r mul self val, and we can return just self times return, self times val. That's it. Good. So that handles multiplication. Now we also have negation. We can just throw that in here actually. So if we multiply by -1, basically, this allows us to do, instead of doing like -1 times tensor, we can just do negative tensor, right? Just add that negative. So that's all this is. So we can return self times -1, and that's it. We, of course, need the matmul, right? Otherwise, we can't really do anything. So here we go, matmul time. And matmul is, again, pretty straightforward. So we've seen this before. We're going to have the output is going to be A at B, right? A at B. So let's do that first. So our output data is going to be np dot is equal to np dot matmul self.data, val.data, right? Nothing crazy. And now it's the backward. The backward pass for matmul is pretty easy. So mul backward input grad. We're going to do if self.requires grad. This can be grad self is equal to np.mapmul input grad and val.data. Oh, input grad, and then val.data.swap axes, right? Transpose of -1, -2. And so remember, dl dA, let's say in this case, is going to be, let's just write it out, dl do at b transpose. That's the formula for our backward pass, right? The derivative of a matrix multiplication, nothing crazy. In the same way, dl dB is going to be A transpose, right? A transpose, and then it'll be dl do, right? That's just how it is. So, and we derive this, right? Hand derive this in that transformer video, right, where we kind of figured out how did these derivatives actually come together, like what was the math that made them happen. So that's fine. And so we're just going to kind of go with it. You can refer to that if you want more information. So again, if grad is none, just like before. So this is going to be a lot of this. Grad is grad self, else self.grad plus equals grad self. And now that we're done, we can do grad self is just none. If val.requires grad again, well, it'll be the same thing, right? So grad val is going to be np.mapmul, and just like we saw, it's going to be self.data, so it's going to be the actual A transpose, so self.data.swap axes -1, -2. We're flipping the last two axes, right? And we'll do input grad, multiply it with input grad, and that's it. So we can do if val.grad is none, then again, val.grad equals grad val. Else val.grad plus equals grad val. And again, we can set grad val to none. We don't need it anymore. Okay. So next step is just like before. Again, I'll just copy this in because it's not that interesting. It's the same code again, right? So go ahead, if it requires grad, this is my mapmul backward, they're the parents. And last one we need is division, right? So division, and that should cover all of our operations here. So we can do def true div self val. Okay. Oops, this should be underscore, right? That's our dunder. So division, again, pretty easy. This is element-wise division, right? So this is going to be basically if O is equal to A divided by B, then dO dA is going to be equal to 1 over B, right? The derivative of O with respect to A, well, A is just multiplied by a 1 over B constant, so there you go. But the more complicated one, but not that bad, dB is going to be equal to negative A over B squared, right? That's the derivative. The derivative 1 over something is just negative that over the thing squared, right? So nothing crazy. So we can again do this. So let's just go ahead and copy this piece in because it's exactly the same as before. So we're going to check for it. Should have honestly made one cohesive code that just did this, so I don't have to repeat it so many times, so that's fine. No big deal, just making this as readable as possible. Div backward, right? So it's going to take some input grad, right? Input grad, the upstream gradient, and it's going to be if self.requires grad. Self grad, like we saw, the derivative with respect to A, which is self, is going to be just 1 over B times our upstream gradient. So it's just going to be the input grad divided by val data, right? Divided by B. And then self grad, just like before. Grad is going to be self dot, again, broadcasted grad accumulate, self dot shape, self grad. And yeah, that's basically it, right? That's our setup. And now we can do if self dot grad is none. Go ahead and do self.grad is self.grad is self-grad. Else self.grad plus equals, right, just like before, plus equals self-grad, and then again self-grad is just, or sorry, oh, my bad, these should, yeah, so it's then self.grad, self-grad is none. We don't need it anymore. And then in the same way, if val requires grad, again, val grad will be equal to the input grad, the upstream gradient, times -1 times self.data divided by val data squared, right? That's my gradient. And then just like before, val grad is going to be self.broadcast grad accumulate, val shape, val grad. And we can do if val.grad is none, we can do val.grad is val grad. Else val.grad plus equals val grad. And we can set val grad to none. We don't need it anymore. And then everything else after that is the same. All right, go ahead and store it. We have a div backwards, and we have everything we need here. And then in the same way, we have our rTrueDiv, which again, division is of course a ordered operation. So if we want self over val, well, it'll come in as val over self, right? Because it's flipped. So there we go. We just flip it already here. Okay. And that covers all of our operations, right? All of the standard set of binary operations, right? So let's just double check that it covered everything in, yeah, okay, good. So up next are unary operations. And these are also very simple, right? Nothing crazy. So we can, let's just close all of these, make it simple. Okay, up next, unary. So these are element-wise operations, right? Unary ops. Let's add some divider. There we go. All right, let's just start with the first one. Easy. Let's just do power, right? Def pal, self, and exponent. Okay. So we know that if O is equal to A to the power K, then dA is just going to be equal to K times A to the power K minus 1. Right? That's standard exponent rule, nothing crazy. And I'm assuming the exponent is not learnable, right? Just to keep it simple. I'm sure there's applications for that. I just don't really care about it, so it's fine. Because we won't be seeing it, so exponent. So just take some data and just use your standard exponentiating. And then our backward will be def pal backward input grad. We no longer have all that broadcast grad accumulate, right? This is just an element-wise operation. There's no broadcasting or anything like that. So we just go ahead and just apply our derivative to every single element of that tensor. So we can do self grad is going to be input grad times exponent times self.data, self, to the power exponent minus 1, right? So we just go ahead and multiply with the upstream gradient, our gradient for this operation, exponent times self.data to the power exponent minus 1, and that's it. And we can do if self.grad is none, then self.grad is equal to self.grad, else self.grad plus equals self.grad. And then again, once we're done with it, we can do self.grad is none. We're done with it. And now that we're done with it, we can go ahead and just, again, this has not changed. It's the same setup. But the only difference is, notice our parent now is just one thing, right? Because if I exponentiate, the exponent is not learnable. So the only real thing that's the parent of this is the self. We don't really care about the exponent. We could put the exponent in here. It wouldn't matter, right? Because our backprop would basically just skip over it when we implement it because it's not a learnable thing. So we don't really need it. Similarly, def exp exponentiating self. Let's do this. To do this, we know e to the power stuff has a very nice property. O is equal to e to the power a. Then we know dA is also equal to e to the power a, right? Nice property of our exponentiation. So we can do out data is equal to np.exp self.data. And then we can do def exp backward input grad. It's going to be if, again, if self dot requires grad, so only if we need gradient, self grad is equal to input grad times out data. Because we know the if the derivative of the thing is just thing, then it's just the output data, right? The derivative of e to the self.data is just the out data. There's nothing else. That's it. And then everything else after that is, again, identical, right? Go ahead and add it in, set it to none, and then there we go, right? And again, our parent, the output of exponentiation comes from just the one thing. There's only one input, right? So it's just self, and that's it. Okay, now log, self. These are actually pretty easy, right? So we can go through these pretty quickly. So output is equal to np.log self.data, right? Just take the log. And then def log backward. We know the derivative of a log is just 1 over the thing. This is assuming natural log, right? So input grad. I should probably write a more generic one for non-natural log, but that's fine. We can do that later. If self.requires grad, self grad is input grad times 1 over self dot data, right? That's the derivative of log, 1 over the thing. And so now we can, again, everything after that is identical. So we are moving fast now, right? So again, go ahead and accumulate or store the gradients, and we have our log backward with just one parent. Absolute value, this one's pretty easy, but a little bit different because as we know, the absolute value function is actually not differentiable everywhere. It's not differentiable at the, the vertex, right? The point, essentially. So when we do absolute value, so we're going to say the output, scroll down a little, close this too, output is equal to absolute value of a. This means dA is going to be the sine of a, where sine of 0 is equal to 0. So all this is basically, we have a, let's see, so the derivative of an absolute value function is either 1 or -1. Right? Because it's just it's just basically our, let's just pull up a figure to make it clear. Absolute value. Images, plot. Right? Here we go. The derivative of an absolute value is either 1 for the positive or -1 for the negative side. And so when we backpropagate, that's all it is, right? The derivative of our absolute value will be 1 for the positive values and -1 for the negative values. And we're just saying 0 for the vertex because we don't really know what it should be, so that's just an approximation. And so let's just do that. This is going to be very easily. Our output is first going to be equal to np.abs self.data. And we can do def abs backward input grad. If self.requires grad, we're going to do self grad is equal to input grad times np.sine, which is 1 or -1, or 0 at 0, sine self.data. And there we go, right? It's just 1 for positive values, -1 for negative values. Everything after that is the same, right? So we have an ABS backward now. All right, now we can do clamping. So def clamp. Clamping is basically taking a matrix or a tensor and then making sure that all the values that are either less than or greater than a specific value are just set to those specific values. So we can do that. We can do self, and this can take a min val as none and max val as none, right? And what we can do is our output is np.numpy, and CuPy called clip, that's fine, self.data, min val, max val. So it's going to threshold essentially our data. Clamping's gradient requires a little bit of just like thought. There's nothing fancy about it, but the idea is that if we have some data like 1, or let's say -10, 2, and 5, and we clamp it between -3 and 3, then technically this will become -3, 2, 3. And the way you can think about it is in our backward pass, we kind of just set these values to something. We don't know what their gradients should be, right? Like what should they be? So basically we do an assumption where we say anything that was actually changed because of the thresholding, we'll just have a gradient of 0 because we don't know what they should be. And anything that was left alone, we'll just have its standard gradient, right? Nothing fancy. So this is pretty easy. We can do def clamp backward input grad. And how this is going to work is if self dot requires grad, we can do a mask, and the mask is just going to be self.data greater than or equal to, so it's a true false flag. So minval, if minval is not none, else negative np.inf, because if we don't provide a minimum value, then we'll treat negative infinity as our minimum value, right? And we can do self.data less than or equal to maxval if maxval is not none, else np.infinity, right? So if we don't set a maximum value, then our default maximum value will just go ahead and be infinity, right? All right, so now what we're going to do is this mask is just going to be our self-grad, our upstream gradient, right? Self-grad grad is just going to be the input grad, the upstream gradient times that mask, right? This mask is just, again, it'll go ahead and zero out the gradient for any values that were thresholded here. And then for values that were not thresholded, the input, like the gradient will actually, flow through. And there we go. Because it's just a true false 0, 1 flat mask, essentially. And so we can do now, if self.grad is none, we can do self.grad equals self.grad. Else self.grad, just like before, self.grad plus equals self.grad. And once we're done, self.grad is none because we don't need it anymore. And we can, everything else after that is, again, identical, nothing fancy. Right, so this is our clamp backward method. All right, up next, let's do the square root. Again, not too hard. Square root. This just takes a self, and square root is just like the exponentiating that we did earlier, but it's just a special method specifically for square root, so let's just have it, because we use square root all the time. So we can do, we know that if the output is the square root of a, then dA is just going to be, let's see, 1 over 2, right? So it'll be 1 over 2 times the square root of a, right? That's the derivative of the square root of something. So no problem. There is going to be a sanity check here, right? So we're going to do if self less than 0 anywhere dot any. Right, so if there's any values that are less than 0, we're going to do warnings dot warn, and we can just copy this in, right? If we give it negative values, that it's going to produce nans, right? And this is obviously going to be an error. Okay. But otherwise, we're good to go. So output is the np.square root data, right? Self.data, sorry. Self.data, just take the square root. And then we can define a square root backward input grad. We're going to do if self.requires grad. We can do self grad is going to be our input grad, right? The upstream gradient times 1 over 2 times, let's put this in parentheses so it's clear, 2 times the np.square root of self.data, right? np.square root of self.data. And technically we could have just used the output here as well, just to save some compute, right? So we don't have to redo that square root again, but it's fine. And now we can do if self.grad is none, we can do self.grad is equal to self.grad. Else again self.grad plus equals self.grad, and our self.grad can be set to none. We don't need it anymore. And now everything after that is again the same, right? Nothing crazy, but now we have our square root backwards. Now we can do our standard trigonometric identities, right? Sine, cosine, tangent. Honestly, I'll just copy these in. There's nothing in these. So As you can see, this is kind of a little redundant, right? I don't actually need to cover all of these methods, but it's just to see how it all comes together. Sine is, the derivative of sine is cosine. So if output is sine, the input, the gradient, will be the cosine of the data times the upstream gradient. Everything else is the same. Our cosine is going to be, derivative of cosine is negative sine. So here we go. Here's us taking the cosine of our data, and in our backpropagation, we're going to do the negative sine of that data. And again, tangent, the derivative of tangent is 1 over cosine squared. So there we go. That's us doing negative cosine squared, 1 over cosine squared for our backward pass. But everything else, identical, right? Nothing crazy. Now what we have is a bunch of these comparison ops. So we didn't really talk about this, but this is just checking, is something equal to something else, right? And we actually used this once, but we haven't actually written it. That's this method right here, .any. And .any just checks, is there anything true in here or not? And so you just need to write a bunch of these comparison ops, which is pretty straightforward. I'm just going to write a simple one here, def compare self other, and the op that we want to do. We'll provide that in a bit. If is instance, other a tensor. If we pass in a tensor for the thing we're comparing to, then other data is going to be other dot data. Else, other data is just data, right? So whatever it may be. It's just other, sorry, other. There we go. And these comparison ops need to also return a tensor. There's no gradients or anything here. And we'll run that operation on self.data and the other data. And requires grad will be false, because of course there's no gradients when we compare if things are equal. So for example, we can do our equal, right? So EQ, this is another method to check if things are equal between self and other. We can return self.compare. We want to compare other, right? So we're going to compare to self our other, and the operation we want is just a simple lambda function. It's going to take some a and b and check if a equal b. And that's it, right? So in the same way, we can just write all of them, right? Equal to, not equal to, less than or equal to, greater than or equal to, and there we go. And then of course we need our any self, and this will just return, and we can use because numpy and cupy already have an any, so this is where we're going to use self.xp.any self.data.array. So self.xp is my backend, right? So whatever this tensor is, if we again go back up to our tensor definition, we wrote this self.xp, that tells us, is this a NP or a CP? So is it numpy or cupy? Or is it on the CPU or GPU? And so we can use the built-in method, right? The built-in or any method already in numpy or cupy and run it on the data._array. Because again, this needs to operate on the array. So remember, there's a couple levels of abstraction. Our tensor has a data thing, and the data is the array, is our array that we wrote. And the array that we wrote has a underscore, so right over here, it has an underscore array that actually contains the numpy or cupy array, right? So there we go. That's just us using an existing any method. All right, so that covers our comparison ops. Now we are on to indexing and reshaping. This is going to be a lot of the same again. So indexing. Here we go. Oh, and reshaping, right? Both of them. So we're going to write a bunch of these. They're all going to be kind of same, and it'll be easy, right? No problem. So you can see individually, these operations are pretty straightforward. Right? There's really not a lot going on here. Just kind of annoying to implement all of them, but we got to do it, so it's fine. Okay, so now we're going to implement indexing and reshaping. It's going to be pretty straightforward. All we need is our, let's just start with get item. So if you remember, get item, we already wrote in our array module a get item method right here that already does it, right? So we will use this for indexing, but we're still gonna have to write the backward pass, right? So that's fine. So we're gonna make sure that if we pass in if is instance, our index, if it's a tensor, oh, is that a comma there? There we go. if the index is a tensor, that's totally fine. We're just going to make sure we unpack it. We're going to grab the underlying array from it. And now what we're going to do is if is instance index, if it's a list or tuple. And when would we pass that in? Let's say we have a matrix like this, 3, 4, 5, 6, and let's say 7, 8, 9. And let's say we passed in indexes like this. So it's going to be a tuple of, let's say, 0, 2, and then 1, 1. So this would say I want the 0th row first column. So that's going to be this row and this column. So that refers to this 2 here. And then 2, 1 says I want this row and the first column that refer to this here. So we can pass in NumPy, right? You can in NumPy and CuPy and whatever. When we index, we can either pass in like one thing of indexes, or we can pass in a list of indexes, right? If we have multiple indexing like this. So that's all. We just need to make sure we handle that exception. We'll do index is equal to tuple. And what we're going to do is just some sanity checks. We're going to do i.data.asType self.xp.int64. We want to make sure we convert our data to int64 because that's what it expects, right? That's what it expects from us. If is instance I tensor. So if it's a tensor, then we need to do this i.data unpacking. If it's not a tensor, if it's already an array, then we can just do self.xp.array I dtype equals self.xp.int64, right? That's it. And we'll do this if is instance I, if it's a list or a tensor. Else I for I in index. So all we're doing, index, IDX. So if it's a list or tuple, we'll just loop through them, right? One thing at a time, right? So for I in index. And if the type of it is a list or a tensor, then lists need to be converted to arrays. So we can do that here using our dot array method. That's fine. np.array or cp.array, no problem. And if it's a tensor, then we need to unpack it, right? We need to do i.data to grab the underlying array and then just convert it to the int64 type. And that's it. That's all that's happening here. If it's not a list or tensor, then there's really nothing else here that we need to do, right? Okay. Now that we have that, we can do our out data is going to be self.data index. So this is, again, when we do this right here, that's going to be calling this getItem method that we wrote earlier, which is just a wrapper again on our CuPy and NumPy getItem, right? Indexing. And that's pretty easy for the most part, getting stuff. The harder part is our backward. So def index backward. And here's our input grad. Now, here is kind of the way you should consider indexing. So let's say we have, let's say we go back to the matrix. So 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8, 9, right? And let's say we take all of this data and we only index out the first row. We only index out the first row. So that's just this row right here. In the backward pass, we're going to get some gradients, right? And the gradients will be in the shape of this thing, right? The gradient's always the shape of the output. So let's say we'll have some D1, D2, D3, right? Those will be my 3 gradients, D2, D3. And the way you should think about this is 1, 2, 3 went forward. This row went forward to do some operations for which we get some gradient. But notice that 4, 5, 6, and 7, 8, 9 did not contribute to this gradient at all, right? These didn't do anything. Only 1, 2, 3 went forward, which means my final gradient should look like this. 0, 0, 0, 0, 0, 0. Because these things did not contribute. So we only really have gradient information for this. And this is how our gradient backward, or index backward, basically works. We initialize a bunch of zeros, and then in the specific positions we index, we place the specific gradients we did. So for example, if our indexing was this, like 1, 5, 9, right? So we only grab the diagonal values, then we'd have D1, D5, D9, and we'd have 0 everywhere else, right? We only want to have gradients copied to the position that they came from. right? Because these are only the diagonal here contributed. That's what we brought with us. And nothing else contributed, so they have gradients of 0. So we can easily do that. It's just a indexing problem. So we can do if self.requires grad. We can do if self.grad is none, then we're going to do self.grad. We're going to initialize everything as zeros. ap.array, we wrote this, dot zeros like, and it's going to be zeros in the shape of our original data, right? Everything is just 0 by default. And the dtype is going to be self.data.dtype. And now we need to convert some stuff. So we're going to do actual index. It's just going to be that index that we had. And we're going to do if is instance index, if it's a tensor, right? That's fine. If it's a tensor, we can just do our actual index is going to be index.data. And if is instance actual index, if it's a ap.array, then we can unpack it one more time. Actual index is equal to actual index.array. So I can start with a tensor, and the tensor will get unpacked to its array, and then the array will get unpacked to its actual numpy or cupy array. If I start with just an array, then we skip over this line and we just go straight here. It'll unpack it to its cupy. So we just want, essentially in the end, a numpy or cupy array. Now what we use is the np.add at self.grad actual index input grad. So we talked about this in that transformer video. We used np.add@, in our embedding matrix, right? So if you remember in embeddings, for example, we could have some embeddings like 1, 2, 3, 4, 5. Actually, let's just call these something else. Let's call them like 1, 1, 1, 1, 1, 1. That's our first embedding. And then we'll have 2, 2, 2, 2, 2, 2. And let's say 3, 3, 3, 3, 3, 3. And then lastly 4, 4, 4, 4, 4, 4. So when we do our embeddings, what we do when we do our embedding matrix, what we're doing is essentially just indexing, right? We're indexing this matrix for the specific rows that we want, right? So if we want this word and this word, then those are the ones that we go ahead and index. And actually, instead of me doing that, let me just pull up the figure so it's super clear about what's going on. Otherwise, it may not be super clear. So let's just pull this up. So this is the figure we looked at then, right here. So we have these embedding vectors 0 through 4. And let's say we want 0, 3, 1, 3, 2, 4. So it's going to index 0, index 3, index 1, and then 3, 2, 4. It's going to index 3. It's going to index vector 2 and index vector 4. In the backward pass, we just have gradients for all of this stuff. And what we need to do is just add the gradients in. The gradient at this position, this location here for this embedding, should go to position 0, embedding 0. The gradients for this position should go to position, vector number 3. The gradient for this position should go to vector number 1. And what makes it a little bit trickier is when you have multiple repetitions of the same indexes, like we can see we use 3 twice, we're going to add to that third embedding, right, this embedding right here, both times, because it gets a contribution of the gradient from here and a contribution of the gradient from here. And np.add@ is just an easy way of doing that. np or cp, right, cupy as well, where we'll just take the gradients, this here, and at these specific indexes, we're going to add these input gradients. And np.add@ makes sure that if we have repeated indexes, right, like in this case, we had 3 happen twice. If we have repeated indexes, it'll go ahead and add multiple times, right? So it'll accumulate the sum for repeated indexes. And that's why we're using np.add@. That's all. Okay, good. So that's our backward pass. Nothing too crazy. Everything else after that is identical. So here we go. Index backward, right? Okay, next one. We need our set item. And this one I'm not a big fan of, but we do need it just in case, but we're not going to worry about it. So we're going to do self index value. Now to set item is we basically take a matrix and you replace the values of the matrix with another matrix. And this is technically an in-place assignment, right? We're essentially just like replacing in place something. And so we're not going to support any kind of derivatives for this. We can do in-place assignments, but we're not going to do gradients because this is not something that we would normally do in our applications, right? So we're not going to worry about it. So is instance index tensor. So just like before, we can do index is index.data. We wrote this We actually already wrote all this already. It's basically like before, but now we're doing those indexes, and then at those indexes, we will place these values, and that's it. So this is in place. Notice we're not returning anything. We're just directly updating the values of self. This supports no kind of gradient propagation because I don't really know what the derivative of this could be for most things. So if you need it, then we can, you can basically write a custom module for that, but this is fine. So up next is the transpose operation. This one's a little bit more important because we're going to be using it all the time. So transposing, so let's just do transpose, and we can pass self and the two dimensions, right, dim1, dim2, that we want to do this transpose on. And transposing is pretty straightforward, right? If we have some data that's, let's say, 12 by 10, and we transpose it, it'll become 10 by 12, right? And if there's more dimensions, then it would be more, but that's fine. So this is our transposing. Now, here's the thing. When we take our data, transpose it, have 10 by 12, this is going to go on to do more stuff, potentially in the neural network, which means in the backward pass, our gradients will be in the shape of 10 by 12, which means for us to make our gradients be in the shape of 12 by 10, we need to transpose them again. And that's basically it. If we transpose in the forward pass, we need to transpose those same dimensions in the backward pass on those gradients, right? So just flip it back. Because again, our gradients will be then 10 by 12. We need to transpose them back to 12 by 10 so they match, because the gradients of our tensor the gradients of the tensor has to match the shape of the tensor. So very simple. Out data is going to be self.data. We'll use the swap axes method that's just built in, and we can do dim1, dim2, right? That'll use our numpy array, cupy array, whatever, their swap axes method. Go ahead and do the transpose. Now we can do transpose backward, which again will pass in some input grad, and all we need to do is transpose the input grad. So we'll do if self.requires grad, self grad is equal to input grad dot swap axes. It'll be dim1, dim2. Just go ahead and flip it, right? So this is just going to go ahead and flip those same dimensions in our thing. So if we flipped dimension 0, dimension 1, then again, if we flip dimension 0, dimension 1, it'll flip those dimensions back to where they need to be, right? Nothing crazy. And after that, everything else is, again, identical, right? Go ahead and accumulate the gradients. We now have a transpose backward. In the kind of same flavor of things, we have a permute, right? And permuting is where you want to transpose multiple dimensions rather than just two of them. So we can do def permute self and dims, right? We'll just pass in our dimensions. And our out data is equal to np.transpose. So transpose in numpy and cupy is permute from PyTorch. And then swap axes in numpy and cupy is the same as transpose in PyTorch. So it's just a little bit difference in naming, but that's fine. Self.data, and we'll pass in axes equal dim, right? So we can pass in multiple dimensions. So here we go. We're gonna go ahead and do that. And just to make this very clear, this is basically passing in, like, if we have data in the shape of 10 by 11 by 12, and we say we want to permute it into 0 to 1, that will create a 10, because the 10 is 0, so that stays the same. But then it'll make 12 and 11, right? 12 and 11. So it'll just flip those dimensions. And so if we do flipping here, we kind of need to do the same thing in the backwards way. So what we need is this 10, 12, 11 to go back to here. If we argsort this, right? So if we sort this, argsort does this. So sorting would just return 0, 1, 2. And that's it, right? 0, 1, 2 would be the sorted value of this list here. But what I want is not the sorted list, but the argsort. So 0 is the 0th index in this thing, so that's 0. 1 is the second index in this thing, so that's 2. And then 2 is the first index, 1. And so if I argsort this, it'll basically provide, and this is actually not that helpful because this is a, let's maybe make this a little bit more complicated. Let's just add, you know what, it's fine. Let's just keep going with it. So this will be the argsort. And if I just go ahead and re-permute my data according to this, it'll put everything back in the same place, right? Because I want 0 first, which will give me 10. And then I want 2 next, which will be 0, 1, 2. That's 11. And then I want 1 next, which is 0, 1, 12. So that gives me 10, 11, 12 back, exactly how I had it before. So that's how we're going to be doing our backward method, right? So it's going to be def permute backward. Again, input grad, and we just need to change this. So we're going to do if self.requires grad. We can do our inverse dims is going to be equal to np.argsort dims, right, dims, just like that. And then what we can do is self grad is equal to np.transpose input grad, and axes will be the inverse dims. And this is, again, it's just going to put everything back exactly how we found it, right? That there's nothing else. So because we did 0 to 1 here, you'll end up with just 0 to 1 again. And this 0 to 1 applied to 0 to 1, so 10, 12, 11. This 0 to 1 applies to our gradient, which will be in the shape of 10, 12, 11. So it'll be 10, 2 is 11, 1 is 12. So we're back to 10, 11, 12 from before, just undoing that permutation. Now that we have that, again, everything else after that is identical, right? That's our permutation. In the same way, we have reshape, right? Def reshape. And in reshape, we'll pass in a self and some shape that we want to reshape to. And so our final data is going to be self.data.reshape. And we'll just pass in that shape, right? And that's it. Now, if we reshape our data to one thing, we need to undo that reshape in the backward pass, right? So for example, if we had a data like this, 1, 2, 3, 4, 5, 6, and we reshaped it to just one tensor, right? One long tensor, 1, 2, 3, 4, 5, 6. So we just flattened it. Then when we reshape it, or when we compute gradients, we're going to get gradients in the shape of this. But we know that these first three values came from the top three, and the second three values came from these here. So I just need to take my gradients, like whatever the gradients of this would be, and just reshape it back into the original data shape, right? Because these, whatever happened here was created by these here. Whatever happened here, whatever gradient contribution came to here was created by here. So we just need to reshape the gradients back into the original data shape, right? So this is, again, very simple. Def reshape backward input grad, and it'll be if self dot requires grad, then we do self grad is equal to input grad dot reshape self dot data dot shape, and that's it. We're just going to take our data and reshape it back in the original shape of the data, right? So whatever the data originally was, just put the gradients in that shape, and everything else after that is the same, right? Nothing crazy. So we have that. Now our flatten. Flatten is, for the most part, pretty simple, but we have to deal with a little bit of annoying indexing stuff. So let's just do it. We'll have a start dim equals 0, end dim equals -1. So flatten is to take a tensor, and then let's say you have a tensor of shape batch by channels by height by width. And we just want to flatten these last two dimensions here. So that's 0, 1. We'll start at 2 and 3. So we'll flatten start dim 2, end dim -1 is just the last one, right? So that'll flatten them. And so we just need to basically do that. And backprop is, again, the same way. We just need to reshape the data back into the original shape. So let's just start with it. So if end dim is less than 0, like if it's -1, then our end dim is going to be equal to the self.data.enddim plus end dim is equal to, right? Because if this is -1, then if our data has 4 dimensions, then the indexes are like we had before, batch by channel by height by width. There's 4 dimensions here. Indexes are 0, 1, 2, 3. And so if the end dim is -1, then it's going to be 4 -1, which is 3, which is going to refer to this, right? Refer to this. That's all. In the same way, we'll have if start dim less than 0, then we can do start dim is equal to self.data.end dim, number of dimensions, plus the start dim. And we wrote this, right? We wrote this method right here, right? It was one of the properties of our array from earlier, right? The last video, end dim, the number of dimensions in our array or tensor or whatever. If start dim is 0, right? So if we're starting at the beginning, and end dim is self.data.end dim -1. So if we're flattening everything, then the final shape, the new shape, will be equal to -1, and that's it, right? It's just one big shape. Else our new shape will be equal to, and this is just a little bit of shape matching. It's just going to be self.data.shape, everything up to the start dim, plus int np.prod, right? So we're going to multiply together all the dimensions that we're going to be flattening from start dim to end dim plus 1, because we need to make it right, we need to include that right position, plus self.data.shape end dim plus 1 to the end. And that's it, right? That's basically it. So basically, if we're saying, if we had these dimensions, like if we had dimension A, B, C, D, E, F, and we wanted to flatten C, D, and E, then basically we'll have dimensions A and B, just like before, and we're going to flatten C, D, and E. So that's going to become a C times D times E flattened. That's why we have a prod right here. And then whatever's left over, which is just F, right, afterwards. And that's it. That will be our new shape. And so out data is just going to be self.data.reshape new shape. Just go ahead and put it in that shape, and we're done. Now for the backward pass, flatten backward. We just need to put our data back into the original shape, right? So there's nothing happening here. This is exactly like the reshape backward from before. We just need to take our data, the gradient, which is in this weird reshaped, not weird, but in this reshaped version, and then just shape it back to the original data shape. So everything matches and we're good to go. And that's our flatten backward. We now have unsqueeze and squeeze, which is kind of like this, but unsqueeze and squeeze adds a extra dimension, right? It's just to add an extra dimension. So if we add an extra dimension, like if we have batch by channels or whatever, and if we add an extra one dimension, which is unsqueeze, then in the backward pass, we just need to get rid of that extra one dimension, right? Just remove it. So we'll do def unsqueeze first. Unsqueeze, you provide a, the thing we want to unsqueeze, and dim, which, where do we want to add that extra dimension? In NumPy and CuPy, they don't actually have a method called unsqueeze. It's called np.expand dims. That's what they call it. And it'll be self.data, and we do axis equals dim, right? That's the dimension we want to do it on. And so def unsqueeze backward is just going to be very simply, we'll have our outgrad, the output gradient, and it'll be if self.requires grad, we're going to do grad is equal to outgrad.sum axis equals dim. So why are we doing a sum? The reason for this is if we had some data that was batch by channel initially, and we made it batch by channel by 1, well, this is just an easy way, because technically we just want to sum up, because this is just a one dimension, so we actually don't need to do a sum, but we just want to accumulate up all the gradients along this dimension, which is just 1. So we could have also just indexed it. It doesn't really matter. We're just going to add up all the gradient contributions here, and we're down to batch by channel. So notice that we don't have the keep dims, right? We're not keeping the dimension, so it'll reduce the dimension on that tensor. And we're just going to quote unquote add all the contributions together, where the contribution is just that one thing. So that's fine. It's just shorthand. So self.grad, again, everything else after that is the same, so we can copy it in. Go ahead, and there we go. That is our unsqueezing. And then in the exact same way, right, we have squeezing. This is the removal of a dimension. So if we remove a dimension in the forward pass, we need to add that dimension back in the backward pass. So we're going to do def squeeze self, and the dim is none. If we don't provide a dim equals, if we don't provide a specific dimension, then we'll remove all one dimension. So for example, if we had the shape batch by 1 by height by some other dimension by 1, if I just do squeeze, it'll automatically get rid of everything that just has a 1, right? Anything with a 1 that'll go away. But if I do squeeze with a -1, the dimension's the -1, then it will specifically get away. Remove these dimensions, right? The correct dimension that we identified. So we just need to do a little bit of a check. Shape is going to be list self.shape. Store that right there. And we can do if dim is none. So if the dimension is none, then our out shape is just going to be S for S in shape if S does not equal to 1. So it's all the dimensions except for the 1 dimensions. Else, if shape dim does not equal to 1. So if we're trying to squeeze a dimension that's not 1, this should throw an error, right? It's going to raise a value error that, hey, you're trying to squeeze a dimension that can't be squeezed because it's not a dimension of 1. And then our out shape is going to be shape dim up to that dimension plus shape dim. Sorry, this should be not shape dim, sorry, just shape. Shape from that dimension +1 to the end. So this will go ahead and basically keep every dimension except for the one that we want to remove, which is a 1 dimension, right? Just a 1. That's our out shape. And so finally our out data is just going to be self.data.reshape. It'll be out shape, and that's it. And then in the same way, our squeeze backward AutoGrad is just going to be a self. Let's do again, if self.requires grad. We're going to do if dim is none. So if we didn't pass in a dimension, then we're kind of good to go. We can do grad is outgrad.reshape. Shape, just put it back exactly how we found it. Otherwise, else, right? If it's if dim was not none, then we only need to reinsert the squeezed dimension, right? The 1 dimension that we had. So we can do grad is equal to np.expand dims, just like we did before, outgrad, and axis equals dim. Because if we only squeezed out a specific dimension, then we only need to add back or expand back that specific dimension, and that's it. And then our grad is going to be equal to grad.asType self.data.dtype copy equals null. This was just a sanity case in case something. Actually, don't know if we need this. I don't remember why I put it in there. I'm sure I was maybe debugging something, so that's fine. If self.grad is none, we can do self.grad is again grad, else self.grad plus equals grad, and everything after that is the same, right? Everything after that's the same. And it should be squeeze background. There we go. All right. All that's left now is chunking, and that will complete our indexing operation. So we can do def chunk self. Chunking is pretty easy. I'll just copy this in so it's easy to see what's going on. Basically, we want to take a tensor and chunk it along some specific dimension, right? So we have this tensor A through G, and I want to chunk it along this, some dimension. In this case, if we do, we have to provide the number of chunks we want. The number of chunks may not be, divisible. So if we say we want to chunk A into 2 chunks, we'll have an ABC chunk and then a DEFG chunk. So it may not be divisible, but that's okay. Actually, to be honest, it's easier if we just assume it's divisible. I can't think of a reason why you wouldn't want it to be divisible. So let's just do it that way, just to make this a little bit easier. We'll do input.shape. So this would technically be, it should be divisible, right? So we will just throw a value error. I'll throw that right here. Yeah, let's just keep it simple, right? Because it's fine. We typically only chunk with divisible stuff anyway. So we're going to go ahead and just take our data and chunk it into equal chunks. We're going to make sure it's divisible. And now what we're going to do is our chunk size is going to be equal to size, right? The dimension we want to chunk up divided by our chunks. How many chunks do we want? And our out tensors is going to be a list. And we're going to create a list of these outputs. We're going to do for I in range chunks. We're going to do start end equals I times, right, chunk size, to I plus 1 times chunk size. And now we're going to go ahead and slice it. So our index by default, we're going to be using slices, right? So Python has this thing called slice. By default, it'll be none for every dimension input.enddim, right? So for however many dimensions we have, we're going to create none slices because we don't want to slice anything on any of the dimensions except for the dimension that we specify. So for example, if we had a batch by 24 by channel or whatever, and we wanted to chunk this into 3 chunks, then we should get 2 different batch by 8 by C, and we should get a list of 3 of them, right? 3 of them, because there's divisible by 3, right? 8 times 3 is 24. So there we go. So that's what we want. And so we don't need to chunk up any other dimension except for the one that we identify, right? So this would be dim equals 1, right? The dimension we identify. And so we're going to do none slices on everything except for the one we want. So index dim for the specific dimension we want, we'll do slice from start to end, right? That's the chunk we want for that one. And so our slice data is going to be input.data tuple index. Just pass it in as a tuple, and these slices will automatically go ahead and slice our data up. Very convenient. Def chunk backward. This is going to take input grad yeah, this will take input grad, but it's also going to take a start equals start and end equals end, just to keep it clear, right? We're going to pass some other stuff in because we're going to create, if we create 3 chunks, each chunk will have its own backward pass, right? So we need to make sure we do that. So we can do if input.requires grad, right? For each one of these inputs, we're going to do grad is equal to input.xp.zeros, like just create a tensor of zeros of input.data, dtype is equal to input.data.dtype, and that's it. That's my gradient initially, just zeros. And here's the thing. My data looks like this. If my data is in the shape of, let's just create one, let's just create a bunch of ones. Let's just create a tensor like this, just with a bunch of ones. So let's create. So let's say we have this thing here, and we chunked it up this way. And that means if we have these chunks here, so we chunked along, so we had 6 things, and we chunked it into 3 chunks, each chunk having 2 things. Well, our gradients will be in the same shape of here. And this chunk right here will contribute to these indexes of the gradient. This chunk right here will contribute to these indexes of the gradient. So for example, the first chunk will only contribute to the top stuff, and everything else will be 0, right? So there will be no gradient information that it contributes to. So we'll just set these to 0. Oh, here we go. Here we go. Cancel. Sorry. Close. Okay. Yeah. So this chunk right here will only contribute to the gradients in these positions. And this chunk here will contribute to only the gradients in this position. And this chunk right here will only contribute to the gradients in these positions. So it's pretty simple, right? We just need to make sure we create some gradients in the shape of our input, all zeros to begin with, of course. And then our grad slice shape is going to be list grad.shape. That's going to be the shape of this specific slice. And then we're going to do grad slice shape for this specific dimension is going to be end minus start, right? That's the shape of this specific slice that we're going to be doing. And we can then do grad slice is going to be input grad dot reshape grad slice shape. So we're going to make sure everything is in the correct shape, because remember, our gradients are going to come in per slice. So in this case, in that earlier example, we'd get I shouldn't have deleted it. Let me put it back again. Let me just copy U and just Control Z a bunch of times. Sorry about that. Let's just put it back. There we go. Okay, and we'll put U back. There we go. Okay, so all we're doing is we're finding out what is the shape of the gradient. And we know that the chunk we're currently processing, right? The chunk we're currently processing is going to be of the shape of one of the chunks specifically. And so I just need to identify, right, which chunk are we currently, where are we? Are we in this chunk right here, which would be 0, 1, or this chunk right here, which would be 2, 3, or this chunk right here, which would be 4, 5. And that's what the start and end tells me, right? The start and end tells me which part of the chunk am I currently in. And then we're just going to make sure the data, the gradients, are in the shape of that chunk so I can accumulate them in. And that's basically it. So you have grad slice. And so now our grad index is going to be slice none, again, times grad times ndim, just like we did before. And grad index dim is going to be slice from that start to end, just like we did before. And then grad tuple, grad index, is going to be equal to that grad slice. So this is me taking my gradients, right? Taking my gradients and indexing the specific slice of the gradients. Everything is initialized as 0 to begin with. But if my gradients were all 1 for, let's say, the top chunk, then I'm just basically taking those gradients for this specific chunk and putting it in the correct position. And then for the second chunk, we'll put it in this position. And for the third chunk, we'll put it in this position. Now, of course, all of this stuff is we'll basically have 3 different gradient tensors, right? We'll have one tensor for the first chunk, which will have all the gradients up here and 0 everywhere else. We'll have another gradient tensor that's going to have the gradients for this one and 0 everywhere else. And then the third one's going to have the gradients only in this one, and then everything else will be 0. But then when we actually accumulate the gradients later on, they all add together and just create one full gradient tensor, right? Because there's going to be multiple dependencies, so we need to make sure we do that. Good. So that basically handles that. That's our grad. And everything else after that is identical, right? So we can then go ahead and accumulate those gradients up, go ahead and store them, add them together if they don't exist already, right? On the input, right? That's the input is the thing that has those gradients, right? It starts at 0, and then we just go ahead and add them in, right? Add them in. And we remember we do this in a for loop, right? Every single chunk gets its own backward pass, right? Per chunk backward pass. So every single chunk has its own parent, the input. And input.grad will be a tensor of the shape of all zeros, right? Tensor of all zeros, or whatever it may be. And then we essentially add in to that tensor the correct indexes of gradients from here. So it's a little bit complicated. I'd recommend going through it once yourself, but we can now keep going. So out tensors dot append out, right? We have multiple of them, append out, and we can now return out tensors. And that basically covers our all of our indexing operations. All that is left now is our reduction and just a couple of those extra ones that I wanted to do, like mask fill. So let's go ahead and start that now. So to do our sum operation, it's pretty easy. This is now actually, let's just put the label. We are now doing reduction ops, right? Reduction operations. So reduction operations involve taking a tensor and doing some accumulation across one or more dimensions. So we'll kind of get an idea with sum, and we'll expand it out to the other ones. Dim equals none, and keep dims equals false by default. And so let's just say we have some tensor like this, right? Let's just get the main idea. We have, let's say, 1, 2, 3, again, 4, 5, 6, and then again, 7, 8, 9, right? That's our tensor. If we wanted to reduce along the 0 dimension, well, that's just basically adding up all the columns, right? So we do 1 plus 4 plus 7, that's 7, 11, 12, 2 plus 5 plus 8, that's 13, 14, 15, and then 3 plus 6 plus 9, which is 15, 18, right? 18, there you go. I think that's right. So this is our sum, right? Along these columns, and that's it. And this would be our forward pass, right? This would be a reduction along one dimension. There's also the option of reducing everything. So we add all the, if dim is none, for example, then we add everything together. So it'd be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Look, we'd add everything together. And that would be our forward pass. And this would go on to do some more operations, right? Operations. Then in the backward pass, right, of course, we're going to have to come back the other way, right? For backward pass, we're going to get some gradients, right? Some gradients in the shape of this. So if we started as a 3 by 3, our gradients are going to be a 1 by 3. And the question is this: how do I distribute these gradients to here? Well, this is actually pretty straightforward for sum, right? For sum, we know that this value right here in the output was contributed to by 1, 4, and 7. And we know sum just copies gradients over, right? So whatever grad we have here, we're going to have a, let's call it D1, D2, and D3, right? Those are my gradients for these three values here, right? In the backward pass. I know that 12 was created by 1 plus 4 plus 7, which means D1, if we remember, if for our sum operation, if we had A is equal to B plus C plus D, well, what is DA? So in this case, A is 12, and B, C, and D are 1, 4, and 7. Well, what's DADB? That's just 1. What's DADC? Well, it's just 1. And what's DADD? Well, it's just 1. So my upstream, basically, we're just copying in our upstream gradient. So if we want DLDB, it'd be DLDA, DADB. So that's DL, D12, D12, D1. And D12, D1 is just 1. So it's just DLDB. I hope that makes sense, right? So we're basically just copying the gradients in. So all we need to do is take these gradients, and I know that we're just going to repeat it a bunch of times. So I know that these gradients will kind of apply to here. So 1, 4, and 7 are just going to get D1, D1, and D1 because those are the gradients, because that's what came in. And then 2, 5, and 8 will get D2, D2, D2. 3, 6, 9 will get D3, D3, D3. And this is just super simple because it's a sum, right? So we know the gradients are just being copied in, right? It's just a copy operation essentially for gradients. So let's go ahead and do that. So we're going to do out data. Out data is going to be self.data.sum, accesses the dimension we provide, or multiple dimensions, right? We could reduce over multiple dimensions at once, and keep dims is equal to keep dims if we want to keep it or not. And now let's write our sum backward. So like I mentioned, input grad, and then what we can do is if self dot requires grad, only for computing gradients, what we're going to do is self grad is going to be np.broadcast to input grad self.shape. So if you've never seen this broadcast to, it's very simple. Let's say we have some tensor, some matrix, and let's say it's np.ones, and let's say it's in the shape of 1 by 3. But I know that if I add it to something that's in the shape of 4 by 3, then this is going to get broadcasted to the 4 by 3 shape to actually add, do the sum. And so we can actually force that broadcast to happen in this way. We can do, let's say a broadcast is going to be np.broadcast to, and we want to broadcast A to the shape of, let's say 4 by 3, because that's the tensor we're adding to. And if we look at a broadcast, you'll see that it basically comes to this, right? Just like that. So no problem. That's basically we took this ones tensor. Let's look at it one more time. We took, and let's print out A, and let's just print a divider. We basically had this ones tensor, and let's say this was our upstream gradient, and we know that we just want to copy this gradient for every single row or whatever dimension we reduced over in our output, right? In the inputs, right? Whatever actually came in. And that's basically it, right? We're just doing that because, again, 12 was created by 1 plus 4 plus 7, which means my D1 gradient here will go to here, here, and here. My D2 will go to here, here, and here. And my D3 will go to here, here, and here. It's a little bit complicated, but nothing too crazy. And broadcast 2 is just an easy way for me to make that happen. It'll copy that gradient over as many times. We could have also used repeat or something like that, but this is easy because if we have multiple dimensions that we're reducing over, broadcast 2 can handle that. And just like before, nothing else is new. We will add this in here, right? Cumulative gradients, that's our sum backward. Now let's look at our cumulative sum. This is a little bit more challenging, but still not too bad. So dim equals none. I'm going to copy this part in because I think it makes it easy to understand what's going on. But cumulative sum is basically I sum along a specific dimension. So if we had the inputs A, B, C, D, that means my cumulative sum is A plus B, A plus B plus C, and then A plus B plus C plus D, right? That's my cumulative sum. Every position is the sum of that element and the previous elements along that specific dimension that we're doing. In this case, there's just one. So in our backward pass, right, we're going to have gradients from all 4 of these things, right? We'll have a gradient for G1, G2, G3, G4. And now think about the contributions. G4 was created by, or basically the element that G4 goes to, was created by these 4 different values, A, B, C, D. G3 was just created by A, B, C. G2 was just created by A and B, and G1 was just created by A. This means when we distribute our gradients backwards, A took a part in every single thing here. And again, sum just copies gradients in. So that means A should get gradient contributions from G1, G2, G3, and G4, right? Because A played a role in A, the second term, A plus B, the third term, A plus B plus C, and the fourth term, A plus B plus C plus D. And so because A showed up in every single one of these terms, it's going to get a gradient contribution from every single one of these terms. So A will get all 4 of them. B, the next one, contributed to the second term, the third term, and the fourth term, which means it's going to get gradient contributions from G2, G3, and G4. C only contributed to the second term and the third term and the fourth term, so it's only going to get contributions from G3 and G4. And then D only contributed to the last thing, so that means it's going to only get a contribution from G4. And that's basically it. It's how we are piping all of our gradients together, because this is all again sum, right? Basically the output, whatever output we had here, let's say this the outputs was like PQRS, D, basically P is just A, so DPDA is just 1, and Q is A plus B, so DQDA is 1 and DQDB is 1, because it's always just 1, because they're just simple sums. And so just like we had done earlier, we're just copying gradients in, right? We're just copying gradients in. We just have to make sure we copy it in correctly. And if you notice here, our input is a cumulative sum, right? Basically, we're doing a cumulative sum. Well, the output is also a cumulative sum, right? The gradient is a cumulative sum because the gradient for A is the sum of everything. And the gradient for B is just the sum of the first three things, right? These three elements. And the gradient for the next thing is the sum of these two elements. So the backward pass is also just a cumulative sum. So we can do that. Out data is going to be self.data.cumulative sum. Axis is dim. So that's going to be fine there. And then we can do a cumulative sum backward. And this can be a grad output. And we can do if self.requires grad, right? Just like always. We're going to do grad reversed. It's going to be np.flip grad output axis equals dim, because we need to flip it around. We need to do the contribution of G4, G3, G2, G1, and then G4, G3, G2, right? We just need to flip it all around so it all lines up, because right now, if we do the cumulative sum, it'll basically be backwards. If we do G1 plus, or let's kind of write it out this way, we have A, B, C, D. We need the sum of these four things to go in the A position, the sum of these three things to go in this position, sum of these two things to go in this position, and then the sum of just this one, right, will go in this position. So if we do the cumulative sum right now, it would be backwards. It'd be G1 would be assigned to this position, G1 plus G2 would be assigned to this position, right? So it's just backwards. So we just need to go ahead and flip it around. So we can reverse it, just flip it correctly on that axis. And then we just do grad input is equal to np dot cumulative sum, grad reversed, axis equals dim, and then grad input is going to be, again, np.flip, flip it right back, grad input, axis equals dim. And that's basically it, right? Nothing too crazy. Everything after that is identical, right? So we just go ahead and flip it around. So this will make it G1, G2, or let's backwards, so G1, G4, G3, G2, G1. We flipped it around. And then we do the cumulative sum. It'll be G4, G4 plus G3, G4 plus G3 plus G2, and then G4 plus G3 plus G2 plus G1. That produces everything, and then we just flip it back. This way our cumulative sum is just in the right order. So in the end, we'll end up with, G4, G4 plus G3, G4 plus G3 plus G2, and then G4 plus G3 plus G2 plus G1. And I know that these four values here need to go to the first term. These ones here need to go to the second term. These ones here go to the third term. This one here goes to the fourth term. So we have to flip it right back around. And that's it. That's all we're doing, just to kind of accumulate up those gradient contributions. Cumulative sum is a little bit more niche. We don't really need it for too much stuff. But let's just keep going. That was just kind of a cool example. Self dim equals none, and keep dims equals false. We're doing the mean now. Now, how is a mean different from a sum? Well, a sum, when we broadcast over a dimension, or when we sum over a dimension, we're just adding values together. So if we do, go back up here, let's say we had this again. Here we go. Let's just go with this example. We just summed over this dimension in the previous term. But now it won't be just 12, it'll be 12 divided by 3, 15 divided by 3, 18 divided by 3. Right? So there's this, because if we're doing the mean along this dimension, then we add up the terms and divide by our constant. And that's basically it. So the only difference between a sum and a mean in the backward pass is we're going to copy these gradients in, but we multiplied by an extra 1/3 term, right? We had this extra 1/3 term built into our system, right? Into our computation. So that means we need to multiply, or divide by 3 for each one of these as well. So when we copy things in, we need to make sure we scale it by that correct factor. Because if we multiplied by something in the forward pass, well, what is if A is equal to 1/3 times B, well, the derivative of A with respect to B is 1/3, right? So we have this extra 1/3 term that we need to do. And it's not always 1/3, it's the number of dimensions that we're reducing over. In this case, there's 3. If we did the mean of the entire tensor, then there's 9 values in here. So then it would have been 9, right? We would divide it by 9. So nothing much changes. So let's go and do it. So if dim is none, if we don't pass in anything, Then dim is going to be equal to tuple, just get it, tuple range len self.shape. So these are all the dimensions that we are reducing over. And we're going to do outData is self.data.mean, outData, self.data.mean. Axis is the dimension we want to mean over, and keepdims is keepdims if we want that. And so our def mean backward is going to be basically our sum backward. We just have that extra step. So we'll have our input grad, and what we can do is if self.requires grad, dims is equal to dim if is instance, dim tuple, else dim. So what we're doing here is just go ahead and create a tuple of our dimensions that we want to do. And what we're curious about is how many elements are there in each of those dimensions. In this case, this is a 3 by 3 tensor. So this has 9 elements in it, right? So if I reduced over everything, if my data was in the shape of batch by 2 by 3 by 4, and I wanted to do the mean over these 2 dimensions here, well, there's 6 elements in this, right? So we would have averaged over 6 different values. And that's basically what we're doing. We're first identifying the dimensions, and then we'll do num vals averaged is equal to average is equal to np.prod, right? We're just going to multiply up self.shape d for d in dims, right? Just multiply it together. If I wanted to take the mean of this tensor over dim 1 and 2, right? Because it goes 0, 1, 2, 3. If I wanted to take the mean over 1 and 2, then I identify position index 1 has 2 elements in it, right? That's the size of that dimension. And position number 2 has 3 elements in it. So that means there's 2 times 3 total elements in that we're averaging over. That's what that is, right? Just compute how many things we're averaging over. And everything else is the same. So it'll be self-grad is going to be, again, np.broadcast2. Broadcast2. We want to take our input grad, which has been reduced, right? We've reduced some dimension, potentially, and then self.shape. It just broadcasts to that. But because we have this extra term here, we need to manage that. We need to account for it. We'll do num vals average, right? Divide by the number of things we actually averaged over. Everything after that is the same, right? There we go, right? So this is our mean backward. Good. Very similarly, we have variance, right? We would need to be able to compute the variance along a dimension. No problem. Keep dims is false. This is going to look a lot like our mean, except variance has one other step in it, right? So if the variance is the mean of x minus the mean of x squared, right? That's the variance formula. Which means the backward formula, we can just take the derivative, right? D variance dx is going to be equal to, well, let's do chain rule. So we have this mean on the outside, which is really just the sum, right? So this is really the sum of all of this divided by n, where n is the number of elements that we have, so no problem. And so we can write this as 2 times x minus the mean of x divided by n times the input grad, right? The upstream gradient. So that's all it is, right? And we have this extra sum here, and we'll handle that in just a second. So very simply, all we need to do is if dim is none. So this is the same as before. If we don't pass in a dim specifically, then we're reducing over every single dimension in the data. And this is just a sanity check, right? If we just call variance without anything else. And so then our mean vals is going to be equal to self.data.mean, axis equals dim, keep dims is true. We're going to keep that true here from default because we don't really want the mean. We're just storing that because we're going to need it later. And then our var vals, right, the variance is going to be, well, self.data minus mean vals. Actually, we could have just used the variance formula, but that's fine. Mean axis equals dim, keep dims equals keep dims, right? So go ahead and compute the variance of our data. And that's it, right? That's all we're doing. And so our variance backward with some input grad, it's going to look just like what we saw. So if self.requires grad, we're going to have input grad broadcast, go ahead and just broadcast it again, np.broadcast2 to the correct dimension, input grad to self.shape, so whatever the original data shape was. And just like before, we can copy this piece right here. We had our check if it's a tuple or not. If it's not, then we can go ahead and compute how many things we reduced over. And this isn't really average anymore. It'll be num_vals. Let's just call it reduced, right? So how many dimensions, how many values did we actually compute the variance over? Because that determines the n, right? The number of values. And so our centered is going to be self.data minus mean vals. So this is to do basically to follow our formula. We know we need the center data, x minus the mean of x. So that's why we just computed the mean vals and kept it aside. That's our center data. And then our self grad will be 2.0 times the center data times the input grad broadcast divided by num vals reduced, right? That's all it is. It's 2 times the center data divided by n. That's our formula for this. Nice. And everything after that is, again, identical. So that's how we can take the backward pass of a variance, right? Not much different from what we had done. Next, max. Max is not too bad. Argmax, so yeah, so we have max and argmax, that's fine. So def max self dim equals none, keep dims equals false. So what exactly is the derivative of a max? And max doesn't technically have a derivative, but it does in the interpretation that we have. So let's say we do 0, 3, 4, 2, 6, right? And when I take the max of this, it's going to pull out 6. 6 is the biggest value. And this is going to go on to do some more stuff, right? Which means we're now going to have a backward pass, right? Some backward pass. And we're going to have some derivative, right? Some derivative. This will, let's call it gradient 1, whatever. And gradient 1 came from this 6. And the only thing in this list of numbers that contributed to the gradient was the 6, which means basically everything else in this will have 0 gradient, except for the one thing that actually contributed to that downstream gradient. And that's it, right? So for max, all we do is we identify what is the max thing, and then in the backward pass, in those positions that we determined that we need a max, we copy those gradients in. And of course, this applies even in the multi-dimensional case. Like if we had 1, 2, 3, 4, 5, 6, and then again 7, 8, 9. If we compute the max along each row, right, then 3, 6, and 9 are the maxes, which means in the backward pass, these will all be 0 gradient because they then contribute it all, and only these will get the gradient information from that gradient vector. If we do it again along the columns, then 7, 8, and 9 are the max values, which means all of this stuff up here will get no grade. It'll be 0 gradient because they then contribute to anything after the max, but these will have the G1, G2, G3, right? The gradient information. So that's all we need to do. So just like before, if no dim is provided, we want to do it over everything. That's no problem. And our out data is just going to be self.data.max. Axis is dim. Keep dims is keep dims, right? If we want to keep that extra dimension. And then we can do def max backward input grad. And this can be if self.requires grad. We do grad is equal self.xp, right? Our backend dot zeros like self.data, and the dtype will be self.data.dtype. So this is just our check, right? So we're going to go ahead and create a tensor of zeros in the shape of the thing that we wanted. And then for the things that were selected to be mask, or the things that were max in along whatever dim or multiple dimensions we selected, those are the ones that we actually put the gradient for, and everything else will be fine. So for example, in this case, the max would have been, let's just make it clear, kind of like this. So if we did them along the rows, it would have been 3, 6, and 9. And then this would have gone on to do stuff. Which means in the backward pass, right? Right, we're going to get a gradient in the shape of kind of the same thing, actually. So it's going to be, let's call it G1. And then we'll have a G2. and G3, right? That's what my backward pass gradient. The gradient would have been in the same shape as the output, and the output was this column vector, so we would have given that here. And now all I need to do is look at this row. Well, 3 was the thing that was biggest, so G1 goes to where the 3 is. 6 was the thing that was biggest, then G2 goes to where the 6 is. G3 is goes to whatever was biggest, that goes to where the 9 is. If we flipped it around, for example, if this was 9 and this was 7, then G3 would have gone to this position right here. Everything else would be zeros, and only the positions with the maximum values will get that gradient information, right? Because that is what contributed. So you create those zeros, and then what we do is, again, just like before, if dim is not none and not keep dims, do input and not none and not keep dims. So if our dimension is not none, so we provided a dimension, and we asked not to keep the dimensions, we just need to make sure we get everything to match here, because we're about to do an indexing. So for indexing, everything has to match. It's going to be np.expand dims, input grad, and dim, right? So if we, in this, so this is a 3 by 3, for example, this is a 3 by 3 matrix. If I just did a reduction along the rows without keeping dim, it would have produced just 3 numbers, right? Just 3 numbers, and that's it. But that's obviously not the shape of our data. We need it to be a 3 by 1, right? 3 by 1 tensor, so it's a column vector. So this is just me. If we did not keep the dimensions, we need to kind of add it back in for this copying operation to be simple, right? So we can just copy G1 into this position, G2 into this position, G3 into this position. Otherwise, our gradients would be coming in like this, G1, G2, G3, like it would have been a flat row vector, and then it doesn't align as easily, right? So we just need to make sure we add that dimension back in if we did not keep the dimension. And we can do now input grad is equal to input grad times np.ones like self.data dtype self.data self.data, and dtype is going to be equal to self.data.dtype. So basically we're just going to multiply by ones. The reason we're multiplying by ones here in the shape of self.data is this will force our input grad to broadcast to match self shape. So that's it. This is just going to take our input grad and just automatically, we could have also used broadcast, but that's fine. This was go ahead and broadcast it to the correct shape that we want. And then our mask is going to be equal to self.data, self.data equal out data if keep dims, else np.expand dims out data and dim, right? So our mask is going to be wherever our self.data equals the out data if we kept the dimensions. Otherwise, we're going to expand it again just to make it match. And so now we can do grad. Oh, we keep doing that. Grad plus equals input grad times mask, right? So we're going to go take these zeros and then just multiply by the mask wherever our self data is equal to the out data. And that's basically it, right? Nothing crazy. It's going to then, everything in here would have been zeros. Everything here is basically zeros where they're not equal, so the things that are not masked, but then the things that are masked, everything in here that's not max is going to be 0 because it won't be equal, and everything that is the max is going to be 1 because that is the max value for that. And so as long as it's a max, it'll be 1. If it's not max, it's 0. And so basically we're multiplying all our incoming gradients with 0 on the non-max position and 1 on the max positions. That's it. And so now we can do everything else after that is identical, right? Nothing else. All right, go ahead and accumulate those gradients up. I could probably write this a little bit cleaner. I'll probably do that later. That's fine. Just to get a general idea of what's going on. Now we have Argmax, and Argmax on the other hand, Argmax self dim equals -1 is Argmaxing is just to find the the index of the max. So for example, if we had 1, 2, 3, 4, Argmax of that will give me 3, right? The third thing, so 0, 1, 2, 3, the third argument or third index is the thing that's max. Argmax has no derivative, right? So there's no differentiating here. So we're just gonna add it in, but there won't be any gradients here. So Argmax axis equals dim, and we can do def argmax backward input grad we're just going to return 0. So we're going to return ap.array.zeros like self.data dtype equals self.data.dtype. Right? There's no gradients that go with argmaxing, so there's really nothing we can do here. And we'll just kind of return it like a tensor, just like we've done. But our gradient, our derivative here, will just be 0. So we can see we don't even use input grad because it doesn't matter. Lastly, we have a mask fill. So these are just the handful of other ops that we need. I didn't really know which one of these they fell under. So other ops, no problem. So mask fill is pretty important for our kind of causal masking for the transformer. So we kind of need this. Mask fill is pretty easy. So mask fill, the idea is we provide a mask and a self mask, like where do we want to place something, and a value. What values do we want to place in those things? So device is self.device, and then requires grad is self.requires grad, and tensor dot build graph enable. Stick those up here. Actually, I don't need to put that up here. I don't know why I did it in the wrong order. That's fine. And so our out data is just going to be in NumPy and CuPy, right? They just call this where. So it's going to be np.where mask.data value self.data. So basically, I want to, with this mask, use these values for where the mask is true, and these values for where the mask is false. And that's it. So this is going to go ahead and just create a new new matrix that has the value at the mask, where I say it's true, and then it'll just use the original data everywhere else, and that's it. And so def mask fill backward output grad. Pretty straightforward. If self.requires grad, just like we saw with the clamp, anything that we just randomly like replace with the value, like in clamp we just thresholded it, but now we're just replacing random values, not random values, but replacing some value into our matrix. This is not really something we can compute the derivative on, right? So we're going to go ahead and our gradients will be 0 for wherever the mask was true. So wherever we inset these values, and then we'll just use the normal gradients for everything else because that's just, that actually came from something beforehand. So our grad is just going to be np.where mask.data 0 out grad. Grad. And then everything else again after that is the same. So we're gonna just place that in here. You'll go right here. That's fine. So there we go, right? That's our mask fill backward, nothing too complicated. We now have sorting and arg sorting. So again, this is pretty straightforward, but def sort self dim equals -1 and descending equals false. And so sorting is pretty easy. If we sort a tensor along some axis, then we need to undo that sort in the backward propagation, right? That's really all it comes down to. So our sorted indices, so we need the indexes, just to make this easier, is np.argsort self.data axis equals dim. So give me the indexes that I need to sort in. And then if descending, right, if we're descending, then we need to take those sorted indices and do a flip on them, right? Because we're doing it the other direction. Sorted indices. And then again, axis is the dim, right? Go ahead and do that. So this gives me the indexes of the sort, and then I can flip it around. And lastly, to actually do the sort, we can just use the np.take along axis self.data sorted indices and axis equals dim. So all this is saying is from this data, I want you to grab these indices in the order that I provided it here from this dimension, right? Because these indices specify some specific dimension. So again, going back to this example right here. So let me just copy you again. Right here. Right, we can delete all of this. Oh, actually, let's delete you. Don't need you. And we can just, so let's just change the order. So this will be 4, let's say 6, 5, and 1, 2, 3 is fine. So if I sort this along each row, right, that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so argsort will just give me some indexes, right? It'll tell me that along this one, 0, 1, 2 it's already in the correct order. So 0, 1, 2. And the next one is going to tell me it's 4, 5, 6. So 0, 2, 1 would be the correct sorting index, 0, 2, 1. And then the last one, it'll be 0, 1, 2. So it'll be 2, 1, 0, right? In the reverse order, T, 2, 1, 0. And those are my indexes, right? My arg sorting indexes that tell me, the position to do the sorting on. And now that we have that, np.takeAlongAxis does exactly that. I want these indexes, right, from self.data, and these are the indexes I want, and these indexes refer to which dimension? Well, the dimension that I want to do it along, right? So 0, 1, 2 refer to 0, 1, 2, 0, 1, 2, 0, 1, 2 along this axis. That's it. So np.takeAlongAxis just lets me do that very quickly. Def sort backward outgrad. Now, what happens if I resort these? If I sort my indexes one more time. So here's 0, 1, 2. That just becomes 0, 1, 2. That's no problem. What happens if I sort 0, 2, 1? Well, it's going to give me 0, 2, 1. 0, 2, 1. And what happens if I sort this? Well, I want 2, 1, 0. So it kind of works out easy when we're starting from 0, but that's fine. If we weren't starting from 0, it wouldn't be as simple. But you can see it kind of ends up being just exactly the same thing. If I sort my index, here, so this is my index. If I sort it or do argsort again on it, it lets me undo the indexing. That's a pretty common trick, right? So now if I do this, I want the second term, the first term, the 0th term. Well, that'll give me the second term, the first term, and the 0th term, which is the 0th term, first term, second term from the original matrix, which is the 0th term, 9, 8, 7. So this, sorting this and then re-indexing it, basically gives me back my original order, right? The original order. And that's what I need for the backward pass. So my inverse indices is equal to np.argsort. Sorted indices along, again, axis is dim, the correct dimension. Our outgrad is just going to be the same thing, np.takeAlongAxis, and I just want to grab the output grad, the outgrad, but at the specific order of indices along this specific dimension. And that's it, right? So I'm just redoing the sort on our indices, and doing the sort on our indices lets me essentially undo the original sort that we had done, and that lets me go back to the original position, because I'm going to get some gradients for this. So remember, this is going to get resorted to 1, 2, 3, 4, 5, 6, 7, 8, 9 when the sorting occurs. That means my 9, so if we put it back, if we do 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That's the result of the sorting. Now I'm going to get some gradients for this 9 position, but in the original tensor, the 9 was here, not at the end, because this is sorted and this is not sorted. So I need to make sure the gradients from here go back here. I need to make sure the 8 gradients go here. I need to make sure the 7 gradients go here. I need to make sure the 6 gradients go here. The 5 gradients go here. The 4 gradients go here. And that's exactly what we're doing, right? I'm saying that I want 2. So this position, right, the gradients for this position comes from 2, which would be this right here, 0, 1, 2. From 1, 0, 1, and so on and so forth, right? Nothing too crazy. It's just undoing that sorting, right? This is a pretty common trick. And after that, everything else is the same again, right? We're going to go ahead and just return that back. Oh, and I forgot missed that. There we go, right? Our device and everything. Okay, that is our sort backwards. Again, in the same way, I'll just copy this in because there's nothing interesting. We have a argsort backwards, right? Argsort. And argsort, again, in the same way as before, argsorting gives indexes of the sort, not just the sort itself. So it's basically this argsort up here. Argsort has no gradient, so we just return zeros back just like before. And that kind of covers most of the operations we care about. There's still 2 left, and we'll kind of add those in just a second. Let's just add a couple other utility functions, right? Some helpful stuff. Def item. So in PyTorch, we can do an item. And what we do is if self.data.size does not equal to 1, because item is only for scalar values, we'll raise a value error, right? Value error, only 1 element tensors can be converted to a Python float or whatever, right? Python float. If it's a CUDA tensor, if CUDA in self.device, that's fine. We can do return self.data.flatten 0, right? So flatten it, grab the 0th element, and we have to do an extra .get, and this is specific to CuPy, right? .get and then .item. So .get will kind of copy it over to a NumPy array, and then we can do .item, and that gives us our value. If it's just a NumPy array, we just do self.data.flatten 0.item, and we're done. So that's just for NumPy. So just a quick wrapper for getting an item. Def as type, if we want to convert types, that's also no problem. We can do self.data is equal to self.data.as type dtype, and we already wrote a as type method, right? In our array module, we have as type right here, right? We already wrote that earlier, so we can just leverage that, just use that to do that, and we can return self. We have def contiguous. If we want our arrays to take up continuous locations in memory, that's fine. We can just use the NumPy methods for that. Self.data is self.xp.contig or as contiguous array, right? As contiguous array, self.data.array, and dtype is going to be equal to self.data.dtype. So this is going to go ahead and just make our arrays continuous. We don't want to call this too often because it is a copy op, so it is, you know, it's not the fastest, but that's fine. This just takes our existing array and makes it contiguous. And then, of course, we need to be able to detach, right? If we have a tensor and we want to take it off the computational graph, that's fine. That's what detach does. And detached is just a tensor. It's just a standard tensor that takes self.data, and it takes our requires grad is false, but everything else will be none. The grad function will be none. The grad function name will be none. The device will be the self.device. We don't want to take it off the device. And we can just return detached. So all we are doing is just plucking the data out of our self, wrapping it in a new tensor with no gradient information, and returning it. NumPy, if we want data as a NumPy array, that's fine. We can do return self.data.as NumPy. That's a method we wrote in our array module. And then def len self. We can return self.shape 0, right? It's just the len just returns the first dimension. And that's basically it for all of our tensors, right? We'll be testing this out in a bit because we still have more stuff. We haven't written the backward pass yet, but there are a couple more operations that we are missing. This is mostly concatenating and stacking. So I create a new file here, new file, ops, because tensors are kind of operations on single things. Like you apply an operation to this one tensor, but concatenating and stacking is applying operations to multiple tensors, which, you know, this one would not support. So we need to write that just outside. The other thing is in PyTorch, for example, we can do tensor.sum, right? That's fine. But you can also do torch.sum tensor. Both of these are valid. And so we're going to add, this is kind of a, you know, this is like attribute access, and this is more like a functional access for those operations. We're going to add those in here as well. So I'm just going to copy this part because there's nothing in it. All we're doing is using all the methods we wrote, transposing, permuting. So this way I can do MyTorch.transpose, MyTorch.permute, MyTorch.reshape, MyTorch.exp ... So this just gives me functional access to all of the exact same things. And you can see I'm just using the methods that we already wrote, right? Nothing crazy. Okay, so now we can go ahead and implement concatenate. Like I said, it's pretty easy. Concatenate. And to concatenate, it's basically the reverse of chunk. In chunking, we take a tensor and split it up into multiple. In concatenation, we take multiple tensors and stick them together, right? So to do concatenation, all we need to do is we're going to pass in a list of tensors. And we have to specify which dimension, right, we want to concatenate on, like normal. If len tensors is 0, like we don't have anything, then I'll just paste this in there. We can just raise a quick value error here. And to do this, it just makes it a little bit easier to just pull these up front. So tensors 0.xp, right? So what is the backend? Either all NumPy or they're all CUDA, right? Otherwise it'll throw a device error, so that's fine. Device is equal to tensors 0.device, right? They should all be in the same place, so there we go. And then requires grad is going to be any t.requires grad for t in tensors. So if at least one of these tensors require grad, then the output has to require grad, right, for backpropagation. So tensor, and of course tensor.buildGraph enabled, right? That's our flag anyway. And now we can create a list of tensors. So tensor list is going to be our t.data for t in tensors. That's going to unpack our tensors and make the arrays. And then our out data, so the final output, right, the out data is just going to be xp.concatenate. It'll be tensor list, and it'll be axis equals dim. There we go. Our sizes is going to be equal to t dot, and this, we're going to need this. And let's maybe make this a little bit clear. So let's say we had some data that was in the shape of like this. Let's say a 2 by 3 by 10. And then we had another one that was 5 by 3 by 10. And then another one that was, let's say, 4 by 3 by 10. And so when we concatenate this together, if we concatenate on this dimension right here, 2, 5, and 4, then we'll end up with a final tensor of 11 by 3 by 10. So what I want to know is in this 11 by 3 by 10, how many samples, or like how many indexes go to the first thing, the second thing, the third thing. So that's all I want to store. So what we're going to do is our sizes, right, the sizes of the things we concatenated together will be just t.shape dim for t in tensors. Now to do our concat backward is pretty straightforward actually. So the idea behind our backward method for concatenation is in our backward pass, we're going to get gradients in the shape of 11 by 3 by 10, because this is the thing that went forward to other operations. But I know in this 11 by 3 by 10, the first two things come, you know, the gradient for these, the first two things here came from here. The gradients of the next 5 things came from here. The gradients of the next 4 things came from here. So we're basically going to take these gradients, chunk them up, grab the first two rows of the gradients, and copy those gradients into this tensor. Grab the next 5 rows of these gradients, copy those into this tensor. Grab the next 4 rows of these gradients and copy those into this tensor. So we're going to take this tensor and just distribute it to the different tensors that, you know, make this up, right? That made this up. So that's the main idea. We're going to just slice these gradients up and then add those gradients to these individual tensors. Doing this is pretty straightforward. We can do offset is 0. And we can do for t size in zip tensors and sizes, right? So we're going to loop through each tensor and what's their corresponding size. And then we can do if t.requires grad, so as long as this tensor actually needs gradient, otherwise we don't care, the grad index is going to be by default, right? So every dimension will be done. There will be no slices outgrad dot enddim. We will not slice any of the things. So in this case, we have 3 dimensions, and we're just going to say we don't really care about slicing anything. But of course, we want to slice this dimension. We want, in the first iteration, indexes 0 and 1, right? These two, basically the samples that represent this part right here, because this is the first 2 that we want to copy those gradients into. So what we're going to do is we're going to do grad index at that specific dimension that we concatenated on. So in this case, it'll be dimension 0. We are going to just set the slice to our offset to offset plus size, right? So this is going to go ahead and say, I am not slicing any of these indexes, so 3 and 10 are left alone, but I'm going to keep specifically offset 0 to 0 plus 2, which is 2. And so it's not right inclusive, so it'll be indexes 0 and 1, which refer to this specific one right here. And as we loop through, right, we're going to advance this offset. So the next one will refer to this, so it'll be from 2 to 6, which will be basically, to 5, so 2 to 5, and then so on and so forth. So let's just keep going, right? So we have, let's see here. So our grad chunk is going to be our outgrad, and we're going to convert to a tuple because it's list right now, and then grad index, and that's going to go ahead and index our outgrad for the corresponding things. And once we've done that, we can go ahead and do if t.grad is none, then we can do t.grad is the grad chunk, else t.grad plus equals grad chunk. And there we go. And now we can do offset plus equal size. We're going to advance it by that size. In this case, it'll be 2 for the first one, 5 for the next one, so on and so forth. Good. So that basically covers our backward pass. Now to do our final part, we need to, of course, convert this to a tensor, right? So our final output will be a tensor with this concat backward method. And we need to store the parent. So we're going to do if requires grad. We will have a out.add parents. Now, what are the parents of this? The parents of this output is all of the tensors that were in here. And this tensors is a list. So we can just unpack him and pass him in, right? So we're going to unpack him and just pass in all the different tensors that produced this specific thing. So those are all the parents for this thing. Good. And we can now return out. Doing stacking is the same thing. So to stack, so what makes concatenate and stack different is for stack, let's say we had like 4 by 30 is our thing. And we have, let's say, 3 of them. In stack, if I stack them, it will automatically add an extra dimension. So it'll make 3 by 4 by 30 if I stacked on the 0 dimension. If I stack on the -1 dimension, then it would have been 4 by 30 by 3, right? So you can specify which dimension you want to stack on and adds that extra dimension in. Where concatenate already has all the dimensions it needs, stack will add the dimension that we specify. And so we can do def stack tensors dim equals 0. And we can do just like before. So all of this beginning stuff is still the same. So let's just put that in here. Right, so same check as before. And now our data list again was t.data for t in tensors. And then our out data is just going to be xv.stack, because NumPy and CuPy have a stack method, on this data list on this specific dimension. And we're good to go. And then def stack backward, it's going to have some outgrad, right, some output gradient. And just like before, we're just going to grab it. Now we know that when we stack it, all the dimensions in stack have to be the same, right? Otherwise stack won't work. So you saw everything was 4 by 30. So we're just going to go one at a time and just grab those things. And so let's just do that. So we're going to do for it in enumerate tensors. Just loop through every single tensor. And we're going to do if t.requires grad. Then we're going to do grad index, just like before, is going to be equal to slice, none slice, because there's no slice on everything, dot ndim. And then we're going to do grad index dim equals I, right? So it's the ith tensor. So again, if we had a 4 by 30 and we had 3 of them, then our final output is going to be 3 by 4 by 30 when we stack them together, assuming we stack on the 0th dimension. And this is basically saying, which slice do we want? Well, in the first iteration, we want this one, which will be the 0 index. In the next one, we want this one, which will be the 1 index. And the next one, we'll want this one, which will be the next index, because they're all the same shape. In our concatenation, we could concatenate things together that have different numbers of stuff, right? So we had to keep track of the sizes here. In this case, every loop just has one of these 4 by 30s, right? So there's nothing really to keep track of here. And so now we can do our grad chunk is going to equal to outgrad, grab that specific slice, tuple, grad index. And we can do, again, just like before, all of this will be the same. Oh, I missed there we go, right? Go ahead, store those gradients. We have our output, and just like before, right? Let's copy it. We're going to store all of the tensors as the parents of this specific operation. Oh, I closed out. There we go, as the parents. And we can return output. Okay, and that finally completes all of our operations. I think that covers everything. Let's take a look here. Where was the slide deck? Here we go. So yes, we did binary ops. We did our unary ops. We then covered our reduction ops. And of course there's more than this, but this covers everything we need for like 99% of things that I can think of. So that's fine. We covered all of this stuff, chunking, stacking, that's fine. And we also did this here. We talked about broadcasting. We talked about all of this stuff, and we are good to go. We also talked about the reference leak, so that's good to go. All right, now for the fun part. We have now written operations that let us do backpropagation. So let's just try some stuff, right? Let's say A is equal to, and actually, before we do that, there's one thing we're missing. We need to add in our tensor factory. Tensor factory is nothing fancy, so I'm just going to copy paste it in. This is basically a wrapper. If you remember when we created this array, we had all of these methods at the bottom, rand-like, rand-end-like, full-like, empty-like, just stuff like that, just to create tensors. We're going to just create, we're just going to create a wrapper on that because this is as an array. We want it as a tensor, right? We want tensors instead. Tensor factory, there's nothing fancy in it. It's just a bunch of these methods that we can paste in, and they're just wrappers on the existing methods that exist already. So you can see here, basically, I write this method called tensor from array that creates an array and then wraps it in a tensor, and that's it. And then we have our zeros, which just uses the ap.array.zeros method. We had our ones, which uses ap.array.ones. We had empty, full, arange, linspace, ... So all of these methods are just wrappers on the methods that we wrote right here. Nothing crazy. I'm just putting that there so it makes our life a little bit simpler just to create some tensors. So let's say A is equal to ones like, or not ones like, let's just do rand. Rand, and let's say it's in the shape of 3, let's just shape of 1, right? Nothing fancy. Shape of 1. And in that case, we just need a 1. If we print A out, we should see some number print out, python tensor.py, right? So it's just some random number, that's fine. And of course we want to require grad is true, right? So there we go, requires grad is true. And we want to push this through a bunch of different operations, basically some subset of these operations that we've already implemented up here. So let's say B is equal to 2 times A, C is equal to 3 plus B, and 4 is equal, or sorry, D is equal to C divided by 4 or something like that. So we print A, print B, print C, print D, we should see that we have a mul backward because we multiplied, we have an add backward because we added, and then we have a div backward, right? Now the important part is we have the full chain. So inside D, we have dot parents, right? We have the parents of D. So D was created from C. So let's check on it. Here's the parent. And we can see there's only one because 4 is just a constant, right? It's not a tensor, so there's no need to store it as a parent because it's not something we care about. It's just a constant. So we have this parent here. It's a weak reference. Okay, let's take a look at it. If we unpack that weak reference, we're going to see, parents, 0. Let's grab that for, there's only one of them. So the parent of the thing was the output of 3 plus b, right? That's this tensor. And then this tensor has its own parents, right? And this one has its own parents right there. And then if we grab it and then index it, right, or basically unpack it, now we're back one more stage. Now we're over here. We're at the mul backward. And you can see we can just work our way back. So inside D, I contain the full computational graph, right? From D, I can backtrack and create everything else. And this is exactly what's going to power our backpropagation. So to do backward, there's a couple of small things that we're going to have to do. The main thing is we need to implement something called topological sort. And topological sort is basically just a depth-first search algorithm that will organize our gradients. And let's talk about this very carefully because this is where I think most people get tripped up. Let's say we have this. So I have a bunch of figures here. We're going to step through the algorithm one step at a time. Then we're going to implement it, and you'll see it's very simple after that, right? So topological sort is an algorithm that essentially is going to ensure that we can order our backward pass in a way that we're not breaking any kind of dependency. So let's just kind of talk about it in this way. I have this, let's say this is my graph, right? Ignore all the gradients for now. Basically I have some input, I multiply by 2, I add 3, I divide by 4, but then I'm going to take A and add it to C to produce my final D. And that's the main idea, right? So that's my operation. Now during the backward pass, well, let's just kind of follow. I can compute the backward pass from D to C, and then I can actually go straight from C to A. and this should be, this should be DC. DA, my bad. Or actually, no, this is correct, No, we're good, we are good. Let's just close you, that's fine. Because this C is, it's the D is equal to C plus A, right? So we can do DD, DA, that's fine. So in the backward pass, we can go from D to C and then go from C to A, but the question is, can I go from A to I? And the answer is no. The reason is, look at our dependency chain. For me to go from A to I need to make sure that I've exhausted all the different paths that come to A first. And have I done that? If I go from D to C and then C to A, I still haven't done D to C, C to B, B to A, right? There's still another dependency path that I haven't explored. And we can actually go ahead and make this full screen to make it easier. There's still another dependency path that I haven't explored. And so that's the entire idea behind topological sort. I want to create an order of which nodes can I call backward pass on, but I want to make sure that before I go on to do like A to I exhaust all the other paths before it. That's the key idea. And this is basically our problem gradient, right? To compute dA dI, I need all of the gradients up to A, all the possible ways to get up to A, and then we can go from A to I. So let's go ahead and start. So the method we're going to be writing is the build topo. It's very simple. The code is like 7 lines, but I just want to step through it because it can be a little bit confusing. So of course, we're going to be starting at D, right? The end. And like we saw, D will contain that history. It has the history of every single operation we did in here through the parents, right? D.parents will show me C and A. So the parents of D, just to make it clear, the parents of D is C and A, because A plus C is what created D, right? The parents of C is just B. It's also 4 because we divided by 4, but that's not that interesting because it's just a constant. The parents of B is A, and the parents of A is just I. So the only thing with multiple dependencies really, or multiple parents, is D, and that's just to keep this simple but interesting. So at the beginning, we're going to call build topo, and we're going to walk through the algorithm. And when we do that, well, we have to keep track of 2 things. What nodes have we visited, and what is my topological order, right? To create my topological sort. And of course, at the beginning, we start at D, so we've visited D, but nothing in the topo order yet. And you'll see how we build that up. So D had 2 different parents, right? A and C. So we can pick either one. Let's just start at A, for example. So what we're going to do is call build topo on A, because we're going to do essentially a depth first search. So we've gone from D, we've jumped all the way to A, and now we're going to call build topo on A and see what happens. Well, we've now visited A, right? So A gets added to our topological order, right? So, or sorry, to our visited. We visited A, so we added to our visited. And A has 1 parent, it's I, right? I. So, okay, that means we can now call build topo on I, like recursively. We just keep going. So we're going to call build topo on I. Once we do that, I is the deepest part of our graph. Remember, this is a depth first search. So if we reach something that has no more nodes behind it, like that's it, then we are done. Then I must be the deepest node because we've gone as deep as we could. So because we see that I has no parents, we've reached the deepest part. This must be the starting point of our topological sort, right? So I must be the starting point because it's the deepest place, right? We need to figure that out. So the starting point for topological sort will be I. And because we've completed this, right, this exhausts this recursion, and now we can go ahead and jump back. We can jump back here. But we see that because I has no more parents, we can now go up a level. But because A has no more parents to recurse into, because A's only parent was I, there's nothing else. Thus A must be the next point, the next part of our topological order, right? Topo order. So we can add A on there. So we had I, we've now added A. Good. And of course, because we've visited I in that last step, we can also add I to our visited. And we'll see why we do the visited in just a bit. And so we're good to go. We've added this A on. And now we're going to go from A, we've completed A, we're going to go back to D, right? Go back to D. So we're going to jump back from A and go all the way back to D again. But D can't be added to our topo order yet. D obviously has more parents that we haven't explored yet. We haven't exhausted everything. And that's C, right? This path, right? This path is something we haven't exhausted yet. So let's go ahead and explore C. And so just like before, we're going to go from C, we're going to call build topo on C. We now visited C, so we add C to our visited. C has a parent, it's B. So we can go ahead and visit B, and this will go ahead and add B again to our thing. Now the thing about B is B's parent is A, but we've already visited A. And if we visited A, we've already recursed down all the paths that come as the parents of A. So in this case, it's just I, but we've visited A. And because A has already been visited, there's no need to recurse down that path again. That'd be a waste of compute, right? Why would you recurse down A when we've already visited A? So we don't have to worry about it. And so that means we're kind of good to go. We can see that the parents of B, all the parents of B, in this case just one, have already been visited. And so we can go ahead and say, okay, so we visited B. Here we go. We can add B to our topo order. We actually should have added B to our visited as well here. I'll fix that later. And then we visited, after we go back up, right? After we completed B, we go up a level. Does C have any other parents other than B? No, it doesn't. So that means C must be the next thing in our topo order. Then we go up to D. Does D have any other parents that we haven't visited? No, of course not. We just did A and C. So that means D has been added. And that's basically it. This is our topological sort, I, A, B, C, D. Sounds kind of dumb, but is super important because we get to now do this. Our tuple order is I, A, B, C, D. To actually do backpropagation, we shall reverse it. We'll reverse the tuple order and it'll be D, C, B, A, I, right? D, C, B, A, I. And the reason is, in our reverse tuple order, we can now say, okay, let's go ahead and call the backward pass on D. Call the backward pass on D. And that's going to create the backward pass from D, 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 C, and then D, 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 A. And then the next backward pass we call a C, which will be D, C, D, B, right? And then the next backward pass we call is on B, which will be D, B, D, A. And the next backward pass will be on A, which will be D, A, D, I. And notice that we have exhausted everything. We've done D, we've gone from D to A in both pathways, right? Going straight back and then using this residual connection. And because both of them are completed, now that we've completed DBDA, we can now go on to do DA, DI. And that's basically the main idea behind topological sort, right? Nothing too crazy. It's just a relatively simple algorithm that lets us pre-sort the nodes on our computational graph to ensure that when I call backward pass on them, I'm not doing anything before I'm not allowed to, right? If I went from D to A and then immediately called DA, DI to get this gradient here, that would be incorrect because I still had this other graph, other part of the graph that I haven't explored. So to make this a little bit simpler, right, so we can visualize this, I created a, it might not be here, so let's just go ahead and new file. Let me just copy. So I have a thing from NetworkX that will make it a little bit easy to just visualize this stuff. And then what we're going to do is implement the build topo, right, algorithm. Let's call this visualize.py. Let's do that there. And what we will delete is all of you. We're going to write you now. So everything else in here is just for, everything else in here is specifically for just creating, like, here's our operation that I talked about, or multiply by 2, add 3, divide by 4, residual connection, return, that's fine. These are just for plotting stuff. So you can look at it. It's not that interesting. It's just a way to plot it. And we're going to basically plot the forward propagation and the backward propagation for this operation. And you can play with this and create other operations if you want to, but we'll do this because that's the example that we've been exploring. So to build topo, this can be relatively straightforward, but let's just create some data first. Let's kind of do it this way. We're going to do from tensor import ones. That's because we haven't really written the MyTorch stuff yet, so we can print our input tensor. This should run without any issues. Oh. Python visualize.py. Yeah, there we go. Requires Grad, so we're good. And we're going to pass this through our easy operation. So print our output. Oh. Right, so there's our output, and it has that add backward in there. Right, and it has an add backward because, well, the last thing we did was an add. So D has an add backward. And just like we saw, we can just unpack it, right? Dot parents, and this will print out, you know, whatever parents this specific thing had. In this case, it would have been the A right here and the C right here, the two things we added together to get D. Good. So this is what we want to build our graph on. To build our graph, what we're going to do is run this build graph method, but for now I'm going to comment out all of you because we haven't written our topological sort yet. Okay. Good, so let's write our build topo. This is very simple. It's just a couple lines of code, but just important. So initially, right at the beginning, our topological sort visited is none and topo order is none because we haven't done anything yet. So just going back to here, just so we can reference it, at the start, our visited will start as none, and then we'll add, you know, the very first node that we visited, and topo order is also none, and we'll populate that as we recurse. So we're going to do if visited is none. Just go ahead and create visited is a set, right? It's a set of things. It's basically a list of the unique, right? So that's why we're using set, so we can keep track of all the unique things we visited. And if topo order is none, which it will be at the beginning, we can do topo order is also an empty list, just like that. And we'll add that in just a bit. Now, here's the key idea. Remember in this stage, so we'll be jumping around these figures a little bit. At this stage, we saw that A had already been visited, right? We've already been there, which means we don't want to recurse down that thing again. So if we've already been at A, just return back the existing topo order. There's no need to kind of recurse down this again because that wouldn't do anything. So we can do if ID tensor in visited, and if you don't know what ID is, that's probably a good idea to just explain here real quick. Let's just do Python. Let's do A is 2, and we can do ID A. It just gives like a memory, right? Basically a unique address that tells me exactly what this thing is, and every object should have a different one, right? So if ID tensor, if the ID of this tensor is inside my visited, that means I've already been to there before. Like I've already visited A, there's no need to do it again. Let's just return the existing topo order. Now, if it's not there, then we visited, and this is where we say visited.add ID tensor. This is me adding for D at the very beginning, right? D at the very beginning. Here we go. We've visited, so we need to make sure it's in our list of stuff that we've seen. And now what we're going to do is check inside every single parent that we have. So we're going to do for parent ref in get adder tensor, and we can do parents just in case, right? So if for some reason a tensor doesn't have parents, this is a sanity check that'll return an empty tuple, just in case it doesn't have it, but it should. And remember, our parent is the parent ref parentheses, right? We have to unpack. These parents are all weak references. We have to unpack them to actually view them, right? To actually see them. And we can do if parent is not none, right? If parent is not none, then what we do is just rerun build topo on our parent. And again, going back to here, that's exactly what we did. We started here, and then we said, okay, we visited D, A is one of the parents. Let's run build topo on A. And then, oh, I is one of the parents. Let's run build topo on I, so on and so forth. But at some point, we're going to hit the end of it, right? The end of it. Like there is no more parents to go. And so this will basically handle that exception. Like, hey, if the parents is none, then we're not running this, right? If the parents is none, so I had no parents, it's the start, it's our leaf node essentially, well then we don't really have to run this, right? And this is gonna be the parent, the current visited, and the current topo order, of course, right? Because it's recursive, we're gonna keep updating those. So once we're done, we're gonna do topo order dot append tensor, right? Once we're done, basically once we reach I has no parents, so I will be the first thing that exits this loop and then actually adds itself to my topo order. And then my topo order now has I in it. We're gonna backtrack once, and then we can add A to it, and then we're gonna backtrack again, but we can't add D to it yet. Reason we can't add D to it yet is because D had multiple parents, right? So we're recursing through those things. And there we go, that is my topo order. We can now print out, let's print topo order right here. This might be not a helpful way to see it, but let's see. So here we go. Here's my topo order. So we have my input, then we have the 2, which is, we had the multiply, then we had our add, then we had our divide, and then we had that second add for the residual connection. And so, of course, it's not helpful to look at it like that, So we can just look at it like this, right? Let's just visualize it and make our life a little bit simpler. Okay, this should work. Let's see. And I need to uncomment you to actually plot it. So again, you can look at the code online. It's just plotting. But here we go. So what we have here is my original leaf, which goes to a multiplication. Then we added, then we divided, and then we added this and this together. So this is my A, this is my C, that summed together to get D. And so in the backward pass, notice that we first call backward here. So 1 and 1. Those are the first two things to call backward. And then the next thing to call backward is 2, and then 3, and then only this A to I, right? The A to the input backward is called once everything else is already called. And that's the key idea. And we can kind of make this as complicated as we want to be, right? So we can, I actually haven't tested the visual looking nice for other ops, but we can just try it. Let's see, we do D is A plus C, and then E is equal to B times D. And let's just like add in an extra like recursion or extra connection. And now you can see we have all sorts of stuff. We have A to B, B to C. C goes to two different places, right? We can, so D is then A plus C. So we have, let's see, let's map it. So we're starting from the input, multiplying by 2. Then we're adding 3, which creates B. Now B goes on to multiply over here later on, right, at the very end. But then B also goes on to be divided by 4. It also goes on to be added to something. And this adding happens between here and here. So both of those happen. And so we can see we kind of have all these interconnections. And in the same way, we call backward on this method first. And then the second backward, so that's going to be backward of these two things. The second backward, notice that this node has, this node has multiple dependencies. I can't just keep going. If I call this backward here, I can't just keep going onto this node here because there's still all of this to go to get there. So we're going to call this backward first, as you can see right here, and then we're going to call another backward, which will kind of do these two right there. Then we're going to do all of these backwards, and then we're good to go to call the final backward right here. So that's the main idea, right? That's our computational graph, forward and backward. And we can basically implement exactly this code in our backward pass. So let's kind of take a look here. Remember that our methods, and maybe it's easiest just to see it right here, we had a grad. So every method has a grad. So let's kind of look at it right here. We had an output. Print the output. Right, that was the output. And we had this mul backward. But that's the name, right? That's the grad function name. But we actually have a grad function, right? We stored them. This is going to be the actual mul backward method, right? The actual mul backward method. And so that's the function we now want to call. So let's go ahead and just start with implementing the backward method, and then we'll come back to this. So let me pull up the reference again, just to make sure I don't make any dumb mistakes. I'm sure there's a little thing that we still need to do, but that's fine. We'll add it in. It's a lot of code. Okay. Binary ops and reppers, check broadcast grad. Okay, so everything is there. Let's go ahead and add our backward. So what we're going to do is def backward, and we want to be able to call the backward method on a tensor, right? Because the tensor has the history of all the subtensors that are the sub computations that occurred on it to build up to it. So it'll take self, and then grad by default will be none, and retain grad is going to be false, right? So whether or not we want to retain grad, and we'll talk about that in just a second. And actually, honestly, for now, let's just get rid of retain grad, because that's just an edge case that we don't really care about. So we're going to do if grad is none, which it will be right at the beginning, then we're going to start. So our starting point for our gradients is just ones, right? So we're going to do grad is equal to ap.array .ones like. And one thing to keep in mind is our gradients will always be arrays, right? Just to keep it simple. In PyTorch, it's a little bit different. The gradients and the data, like everything is just a tensor, but there's no need to do tensors for this stuff here because it's we don't need gradients on the gradients, right? So it's fine. We're just gonna use arrays for the gradients, and it'll be no problem. And it'll be in the shape of self.data. And then dtype is equal to self.dtype, and then device is equal to self.device. So what we're doing here is basically at the beginning, when we compute our gradients, we need a starting point. And the starting point is 1, because we're going to end up doing chain rule, right? So we're going to, let's say, right here, right? We're going to do do dz, dz dy, dy dx, dx dw. And we're going to multiply all these chain rules together, but we need a starting point. And the starting point will just be 1, so it'll just be 1 times this, times this, times this, times this. So just a starting point. And the starting point will be in the shape of the data, and by default that should just be 1 value when we actually do it, because the loss is just 1 value. So there we go. Okay. And self.grad, so the grad for this specific thing is just grad, because we're at the very end, right? So that's our starting point. And that's assuming we don't pass a grad in ahead of time, right? So if we don't pass it in, if we do, then we would use that instead. But if we don't, then by default, we'll just stick with ones. And so now let's create our visited, just like we did. Visited was a set, and our topo order is also an empty list, right? And that's what we want to populate with our recursion. So let's just write that build topo method that we just wrote already. Diff build topo t, and we're going to do if idt in visited. Well, then we can just return. There's nothing to do here. We're fine. Otherwise, we'll do visited.add idt. And the reason we're not returning topo is because all these variables are outside this. So if we don't do anything, nothing will happen to this, right? This will just stay as is. If we append to it, then we'll append to it. So this is kind of like a global variable for this function. Then we're going to do visited.add idt, right? We've visited this specific thing. And then our parents is going to be, just like before, get adder t parents empty list, just in case. And we can do if parents is none, right? So if we don't have them, then we can just do our parents is just an empty list and just leave it for like that. And we can do for parent ref in parents, which in this case, if it was an empty list, this wouldn't do anything. We're going to do our parent is a parent ref unpack it, just like we talked about. And we can do if parent is not none, then we can do just run it again. Build topo recursively on this parent. And after we're done, we can do topo order dot append t, right? Once we've exhausted all the parents and there's nowhere else to recurse, then we can go ahead and add it on and then recursively work our way back. And so we can then go ahead and run build topo on self. And that's it. That's going to create our topological sort. Now that we have that, remember that we talked about the way for us to do backprop now that everything is in the correct sorted order, all we need to do is reverse the topological order and then just call backward on each of those nodes, and we've defined the backward method for all of those nodes, right? So there's no problem. So we can do for t in reversed topo order, right? Reverse topo order, no problem. We can do if t.grad function is not none. So if that tensor actually has a grad function, then we can run t.grad function on t.grad, right? This is basically us. If let's take add, for example. T.grad is my current upstream, it's my current gradient. And I'm going to take that and pass it in as the input gradient to perform this gradient operation, right? Whatever this is, for all the different operations we have. In this case, it's the add backward, but we wrote all of these for all these different methods. And these are the methods that are now going to be called add backward, mul backward, map mul backward, whatever it may be, just all these methods. And now what we're going to do is if, let's see, if get adder, what's the best way to do this? Let's actually add in some. Okay, so let's maybe just kind of simplify this a little bit. This will go ahead and compute all of our gradients and we're done. But let's just add in a couple of flags here just to make our life a little bit easier, and maybe not easier, but just closer to PyTorch, right? So remember that we have up here a, we actually didn't add it in, so let's add it in now. We can add in a retain grad equals false flag. So we can do self.retain grad is false. So by default, when we do backpropagation, let's just let's use Sigmoid as an example. when we do backpropagation, right here, right? When we do, remember, we had to cache, right? So they're stored as closure variables, but either way, we had to cache these variables in the forward pass so we can use them in the backward pass, right? And the thing is that once I've kind of computed this gradient, I no longer need this. I don't really need any of this stuff, right? I'm done. I can just keep going, which means I should just go ahead and delete this extra, all these extra cache. What we don't want to delete is the cache with respect to parameters we want. So what we're going to do is essentially once we're done using a gradient like this one, and we're on to here already, we can just go ahead and delete previous gradients. We can delete previous we can delete all this extra stuff. We don't need it. We only want to delete it though if we specify it. So by default, of course, we want to delete it. It'll save memory. But in PyTorch, you can do a retain grad is false, right? So we can specifically say, I want you to keep the gradient. I don't want you to just release them, because PyTorch will just go ahead and release them. And if you add this flag, then it won't release them. So let's just add that in. Retain grad is false. There we go. And so let's just add in a quick flag here. Nothing too crazy. So we're going to add that. Let's add it right here above the backward, just so it's clear. Redef retain grad self. And we can throw a quick warning here, right? If we say that we want to retain grad for some reason, then first of all, so on a tensor, we can say we want to retain grad, and we can just throw a quick warning saying, hey, we're retaining the grad, intermediate gradients will not be cleared. This will lead to higher memory costs. And then this is done, right? So we've done one warning, so we don't warn over and over again. And we can do if self.isLeaf, we can just return. So leaf tensors will always retain grad, because leaf tensors are things that are our starting point. And starting points are things like our weights and biases, right? These are gradients. The gradients for the weights and biases are stuff that we have to keep, right? Because those are our grads, right? The gradients of this is what we want in the end. What we don't care about is the gradient with respect to y, c, h, a. We don't care about any of those intermediate gradients. We only need these gradients here. So these are leaf tensors, so those will always be there. So if they're a leaf, then we can return, because that was going to happen anyway. Otherwise, we can do self.retain grad is true. That means we've enabled gradient retention for this specific thing. And so now that we've done that, we can just easily update this. So by default, this will go ahead, compute all the gradients. Once we've computed a gradient though, we would like to just go ahead and drop references immediately, right? Because we don't need them anymore. So we can do retain this is, let's say, get adder. T, if it has, it should retain grad flag. By default, it should be false, right? We never want to retain grad, or retain graph, or retain, oh, can't spell, graph. And that'll be a flag from up here. Retain, and PyTorch does this as well, right? This is by default false. If we do a retain grad, that's going to retain a gradient of a specific operation that we say. If we say retain graph, that will keep the entire computational graph. We will not drop anything at all, which obviously isn't recommended, but that's fine. If not, retain this. Oh, I spelled retain wrong everywhere. Okay. If not retain this, like we don't want to keep it, that's fine. We're going to do the grad function will be reset back to none. This will go ahead and delete all of those grad functions, right? So the grad function had the reference to those tensors. Now they're gone. T.parents is none. We don't need the parents of this thing anymore. Remember, we did this in topological order. So whatever parents, in this case, right, like whatever dependencies we had to do our backpropagation, right here, we've already cleared them, right? So whatever are the parents, we can just go ahead and delete them, the references, and then basically we have another reference that stores C, and then we can clear it. We have another reference that stores B, we can clear it, ... So just go ahead and clear all of our references because we don't need them anymore. And if not, T.isLeaf. So if it's not a leaf tensor, then we can do T.grad is also none. This is basically deleting everything that we don't need. For non-leaf tensors, so for everything that isn't a weight and bias like we saw, right over, let's go back right here. So everything that isn't a weight or bias, their .grad can be none, right? We don't need them anymore. We can delete them. So we don't need the grad for Y or C or K or H or A. These intermediate gradients, I've already backpropagated past them. So if I'm already past them, I don't need them anymore, right? So I can just keep going. And so that clears those out right here. And then again, we don't need the grad function or the parents if we don't want to retain them. If we do want to retain them, then we will have that, and that's fine. And so this is basically it. This is our backward pass, as simple as I could make it. So we can give this a quick try. Let's do, let's change our easy operation here maybe. Let's just make it, let's just do 1, and let's actually just do it right here. Let's do it in Tensor. So we're going to do a is equal to 1s, it'll be 1, and then requires grad is true. So if we again print a, we should see, not visualized, so Python tensor.py, we should see that. And so now if I do b is equal to a times 2, and if I print b, I should see that it's a 2, with the mul backward as its grad function. So if I print b dot, or a dot grad, right, what's the derivative of b with respect to a? This should currently print none, right, because there's nothing there. But if I call b dot backward, and I print a dot grad, now we can see, and okay, looks like we have some bugs. Let's fix them. So this is going to be the mul backward, right? So let's do mul backward right here. And it looks like we have the bug at, let's see, we have, oh, these should be np.multiply, right? So these will be comma, comma, there we go, right? So we're not multiplying there. This is the multiply function, my bad. Okay, so let's try this again. There we go, which makes sense. The gradient should be 2 because I multiplied by 2, right? So the derivative of, if a is 2, if b is 2a, then dBdA is 2, and that's basically it. Let's try something a little bit more complicated. Let's say c is equal to, let's say b.exp, right? And so now let's do c dot backward. Then we should see a dot grad, and we can also print a b dot grad. And we can do that before and after. Both of them should be none. But then we get this stuff here. And this is where you start to see some of the, what I mentioned. Notice that a.grad printed something. A is the beginning, right? The very starting point. And the starting point is always a leaf. A leaf tensor is determined by the fact that this has no grad function because there's nothing that it came from, right? A is created. So a.grad, no problem. We have that right here. b.grad is none. And that's because our backward method will automatically just delete them, right? We don't care about those intermediate things. Why would I cache or want to hold on to what b.grad and all of that stuff is when all I really need is a.grad, right? The derivative of the output with respect to the input. So that's a memory saving technique. And so how do we keep them? Well, there's 2 ways, right? Like I mentioned, we had the retain graph is true. Oh, true. That's going to go ahead and keep them. There you go. And you can see that basically, you can see it's just a multiplication of 2, right? That extra 2 factor. So that's one way of doing it. We can, that will keep it for every single operation. Or we can do, we can say b.retain grad, which will go ahead and run that method, which will throw that warning saying, hey, look, I am trying to retain a grad. All intermediate gradients may not be cleared. But it gives the same values, right? So we can basically specify that I want the gradient specifically for this tensor to be kept because I want to look at it for some reason. And that is kind of it, right? I mean, we can come up with more complicated stuff. So let's do a is rand n. Let's do a shape of 10 by 20. And then let's say w is rand n, and it'll be 20 by 50. And let's do y is equal to a at w, right? That's a standard matrix multiplication. So if we print out y, we should see our date at a little bit too big. Let's make it easier. 4 by 6, 6 by 8, right? There you go. That's our output tensor. And so now I can do y dot backward, print print a dot requires grad is true. Requires grad is true. So now what we have is 2 different tensors that both require grad having some operation in between them. That's also no problem, right? We can print out. Let's print a print w. And after we call dot backward, we can print a.grad, and print w.grad. And what we should see is, actually let's make the numbers even smaller so it's easier. 2 by 4, 4 by, let's say 5, right? Oh. There we go. So we have our data right here. We did a at b, and the derivative is basically exactly how we set it up, right? Nothing too crazy. So we are able to successfully compute all the derivatives that we need to do, right? Yeah, so we can see we have grad for both a and w, right? Both operations have gradients because both of them are enabled to have gradients. If we add more stuff to this that don't have gradients, then those won't be tracked. And that's kind of it, right? So you can create a composite. So let's try Sigmoid, right? Let's do Sigmoid. Let's do def Sigmoid, and let's do x. And the Sigmoid of x will take, we're going to return 1 over 1 plus e, or let's do negative x dot exp, right? We're going to exponentiate that. So again, rand is going to be rand n. We'll do a shape of, let's say, 3 by 3, whatever. Requires grad is true. And then we can do sigmoid of the rand. Let's print that as the output. And there you go. That's the sigmoid output. And so if we do output dot backward, and then print rand.grad, we should see the gradients, right? There's the gradients for my sigmoid. Now, one thing we can try is output times 1 minus output. And notice that we get the same values, right? This is the gradients through my AutoGrad, 0.22871, 0.22746, dot, dot, dot. But this is the gradients from manually computing, or like actually computing the gradients, because I know what the gradients of this is. I know the derivative of my sigmoid is the output of sigmoid times 1 minus the output of sigmoid. And notice that you get the same values regardless. And this is where we're going to have to start to play the game between manual grad and AutoGrad, because AutoGrad's awesome, but notice that for me to do the derivative here, I need to take all of these intermediate steps, right? I need to do all of these intermediate backward methods. And this is where it becomes really important for future stuff, right? We want to write not only AutoGrad-based methods like this, but also we want to write manual methods. So let's just do one of them today, just to get a little bit of intuition for what's coming. And then we'll be focusing on this next time, because we actually have to write modules, right? We only have something that can compute AutoGrad. We don't have any of the other machinery that we need to actually do deep learning, right? So there's still more to go. So for sigmoid specifically, what we need to do is very simple. I'm going to say auto equals true. We'll write this method again in the future. And we can do if auto, then just return it. And our tensor will go through all this stuff. It will do its, whatever, and it will track gradient so we can compute backward. On the other hand, we can kind of do what we've been doing up till now. We're going to do xcp is going to be x.data. We're going to unwrap. So we're going to essentially write the same backward methods like we've done before. We're going to write a forward, like how do you actually compute this stuff on the data. We're going to write a backward method, and then we're going to return a tensor that has that backward method nested in it. And so let's say xcp is xdata. Out data is going to be 1 over 1 plus np.exp negative xcp. So this goes ahead and computes that forward method, no problem. Now the backward method, def sigmoid backward, grad output, right? So we're going to go ahead and write that. And we grad input is going to be equal to the grad output times, I know the derivative of sigmoid is out.data, times 1 minus, and parentheses, 1 minus, 1 minus, or it should be out data, not out.data, out data, times 1 minus out data. And then x.grad, if x.grad is none, then go ahead and do x.grad is the grad input. Else x.grad plus equals grad input. Accumulate those gradients up. And then we can do our, this is kind of all the same as before, right? Except now we have a specialized sigmoid backward. So now when we do this, we have this output. Right now our output is doing, and let's see what it's set to. Auto is true by default, okay. Output right now is this div backward, because the last operation we did was the 1 over, right? 1 divided by all of this stuff. But if we set auto to false, where we're going to actually use these methods, we should see it say sigmoid backward, because we have specially implemented the backward method for this operation. And now we can call output.backward, and everything will work just like normal, right? It's going to go ahead and trigger that backward method, and we can print out the rand.grad, right? So there you go. Those are my gradients. And this is basically what I'm talking about. We want to write these methods, and for known composites, when I know exactly what the derivative of all of this stuff is going to be, there's no reason of using our recursive backward method to kind of, you know, go through all of this stuff. No point of it. We can just manually specify it here and we're good to go. And so high performance neural networks have a mix of flexibility and performance, right? We need flexibility so I can easily prototype. I want to be able to define methods and stuff like that. But if I'm in PyTorch, if I'm using things like Sigmoid or Softmax or just, you know, existing functions that exist, you know, existing functions that already are built into PyTorch that are not custom, then PyTorch should be offering the most efficient backward pass already built in. The derivative of the Sigmoid function will never change, right? No matter what I do. If I'm using Sigmoid specifically, it'll never change. So there's no need to backprop through all of these operations, right? All of these things here. Let's just do it manually. And so that's what we're going to start working on next time, right? We have a ton of layers, actually not a ton. We have a lot of layers that we need to implement. They're going to essentially be everything we need for the GPT-2 architecture. There's going to be a couple other stuff, and then we're going to get into fused operations and all sorts of fun things. We are going to, again, build a neural network structure. And let me just give you a good idea of what to expect, right? So if we back out here, if we go to MyTorch, and we run bash, not run scripts, we can do train gpt2.sh. And what we want to do is train out open web text. We want to be able to do it in fused operations using Triton kernels. And we want to be able to do mixed precision, right? This is precision. And also we want to be able to train on multiple num GPUs is 2. And so I have a bash script that basically lets me pass in all these arguments. But this is our end goal, building a system that can do this. Fused operations, mixed precision, multiple GPUs. And we can see that. We can see it'll kick off training in just a second. And this actually won't even be that fast. We should enable Triton auto-tuning, right? Auto-tune. Let it kick off training. So we can use NB top. And we should see Triton auto-tune just takes a second to spin up. That's fine. But once it does, it should move relatively fast. It's about 20%, 30% slower than PyTorch, but that's kind of awesome given that we haven't really written any C or C++ code or any specific CUDA code. This is just all running in Python, right? So everything's Python based, which is the whole point of this. So let that kick off. That's fine. We're going to start to see, right? Memory on both GPUs are being utilized. Again, the memory cost here is a little bit higher than what to expect from PyTorch, but of course, PyTorch is way more optimized than we have implemented here. But this is basically exactly what we've talked about. It's a mix of our AutoGrad and our AutoGrad and manual grad. So we're going to be seeing all of this stuff come together in the future. So I will see y'all in the next one.